Microwave and Technology Society student branch chapter under this student branch. I would expect that BPPIMT student branch and its chapter will remain active for the future days, and student branch counselor would guide the students to write projects and events funded from IEEE MGA, that is from USA. There are several calls for proposal released mostly from February to April for various educational activities and site programs. I hope everybody knows, especially students should know about the site, the special interest group for humanitarian technology. Every student branch and chapter should do innovative projects for helping underserved people of our society with the direct earning from IEEE USA. As you know, IEEE deals the technological advancement for humanity. Today's student will be the future leader of our IEEE. You need to learn the scope of IEEE activities and ethical values to be practiced. At present, Kolkata section have 5 subsections, 30 chapters. Few of them are joint chapters and societies. There are more than 100 student branch, few are dormant and few are active. 70 to 80 student branch chapter in Kolkata section under 5 subsection 2. Coming to today's program on ChatGPT, which is a much discussed topic over the past years. I am eager to listen from today's learned speaker from Professor Bhattacharyya and Shagotam Das. I know very little about ChatGPT. Only I heard that it is a advanced language model based on GPT 3.5 architecture, generative pre-trained transformer with advanced capabilities to create several educational applications that can transform students' traditional learning experiences and thereby expect learning more accessible and effective. I am waiting to listen to Professor Bhattacharya on the issues of opportunities and challenges. But I shall request Professor Bhattacharya to add the ethical aspect of every opportunities. As we know, every willpower of human being attached to ethical values without which there is no meaning of having willpower. Willpower has to be driven by positive power bearing ethical values. Overuse of ChatGPT or AI model may lead to a situation of technology dependency for simple problem, reduce power of ethical thinking. At least human behavior must not like machine without emotion. But there may be some help. I understand ChatGPT may help more accessible learning for the student with disability. GPT models allow to build intelligent, interactive voice assistant, but like every model I heard, ChatGPT has limitations too, like repetition, redundancy, lack of creativity, and wrong data creation or generation. For successful utilization, one has to know its limitation too. I love to listen in this regard from today's valued speaker. Before concluding, I would like to thank Professor Navnita Das, Professor Debashish De, Mr. Shubhamay Chakraborty for cooperating and arranging this very time-relevant seminar with IEEE Kolkata section. Thanks to BPP, MT Management and Student Branch for hosting this seminar at your institute. Hope participants will learn very valuable aspect of ChatGPT, which creates a madness in every sphere of learned society. I wish the success of this program. Thank you all for your patience and attention. Hope participant will learn very valuable aspect of ChatGPT, which creates a madness in
Thank you,
every
ma'am,
sphere
to
of
inform us
learned
about such
society.
opportunities
I
under
wish
this
the
IEEE
success
community,
of this
and it will be our great
program.
pleasure.
Thank you all for your
Now,
patience and
Mr. Shoma
attention.
Chakraborty sir, the chair of COMSOC chapter, is here with us, and I would like to request him to enlighten us about the IEEE COMSOC Kolkata community. Thank you, ma'am, to inform us about such
Sure.
opportunities
Good morning,
under this
everyone.
IEEE community,
It's an
and it will
honor
be
to be
our
part
great
of
pleasure.
this symposium today. I would first
Now,
like to share my
Mr. Shoma
sincere
Chakraborty
gratitude
sir,
to
the chair
Professor
of
Dr.
COMSOC
Sutapa
chapter, is
Mukherjee,
here with
Principal
us, and I would like to
BPPIMT,
request him
for
to
allowing us
enlighten
to do
us
this
about the
event in the
IEEE COMSOC
premises.
Kolkata community.
Thanks to Dr. Navanita Das and Dr. Devashish De for working out the
Sure.
details of
Good
this
morning,
event
everyone.
after discussion on this
It's
less
an
than a
honor
month
to be
back
part of
actually
this
in COMSOC
symposium today.
Executive
I would
Committee.
first like to share
Thanks
my
to Professor Itisha
sincere
Mishra,
gratitude to
Chairperson,
Professor Dr.
IEEE
Sutapa
Kolkata
Mukherjee,
Section,
Principal
for sharing her
BPPIMT,
blessings
for
in
allowing
conducting
us to
this
do this
event.
event in the
Thanks to
premises.
Professor Chiranjib
Thanks
Bhattacharyya
to
and
Dr.
Professor
Navanita Das
Swagatam Das
and Dr.
for
Devashish
taking
De
time out for this
for working out the
session
details of this
and
event
enriching us
after
with their
discussion on
thoughts.
this less than a month
Now,
back
about
actually
IEEE
in
COMSOC,
COMSOC
it's one
Executive
of the most
Committee.
vibrant
Thanks to
communities in
Professor
IEEE
Itisha Mishra,
family.
Chairperson,
We work
IEEE
on
Kolkata
various
Section,
initiatives with the
for
students
sharing
throughout
her
the year.
blessings in
We have
conducting
tech
this event.
talks, hands-on
Thanks to Professor
workshops,
Chiranjib
sponsored tech
Bhattacharyya and
events,
Professor Swagatam
conferences,
Das
awards,
for
etc.
taking time out
throughout the
for
year.
this session
One of our
and
major
enriching
focus
us with
area
their
is
thoughts.
industry academia
Now, about
collaboration.
IEEE
I
COMSOC,
personally
it's
come
one
from
of the
industry,
most
and
vibrant communities
we
in
feel
IEEE family.
ChatGPT is probably
We
going
work
to
on
be one of
various
the game
initiatives
changers
with
for
the
the
students
industry,
throughout the year.
and
We have
it's
tech
already being
talks,
used or
hands-on
abused in various
workshops,
ways
sponsored
in
tech
various
events,
fronts already.
conferences, awards, etc.
Plagiarism is one of the
throughout the
issues that
year.
are being pointed out,
One of
and
our
the
major
need of
focus area is
regulations,
industry academia
how to
collaboration.
restrict
I
that or how
personally
to
come from industry,
mitigate the
and
risks are
we
already
feel
being discussed even at the
ChatGPT
senior
is
most
probably
levels
going
of
to
the
be one of the
governments.
game changers
Ministries
for
are
the
also
industry.
deliberating
And it's
about
already
how
being
to
used or
make
abused in
checks and
various
balances
ways
on this.
in various fronts
So we
already.
look forward to the deliberations
Plagiarism
in the
is one
next
of the
few hours
issues that
from
are
the
being pointed
dignitaries.
out, and the
Before I
need of
conclude, one quick
regulations,
note: Dr. Wasim
restrict
Arif,
that or how
Secretary
to
of IEEE
mitigate the
COMSOC Kolkata
risks
chapter,
are already being
is there
discussed
in
even
the
at the senior
venue.
most levels of
If
the government.
you need any
Ministries are
details
also
on how to become a member
deliberating
of
about
COMSOC,
how
please
to
get in touch with
make
him.
checks and balances on this.
My sincere thanks to all the
So we'll look
dignitaries,
forward to the
volunteers,
deliberations in
and
the next
best
few
wishes
hours
to the
from the
students.
dignitaries.
Thank you.
And before I conclude, one quick note: Dr. Wasim Arif, Secretary of IEEE COMSOC Kolkata chapter, is there in the venue. If you Thank you, need any
Sure.
sir, for
Thank
your
you.
details on
Thank
how
you.
to become a member of
Allow us to
COMSOC,
proceed
please
ahead.
get in touch with me.
Finally,
Now,
now
I
I
would
would
like
like
to
to
request our
request
esteemed
our
professor,
esteemed
Dr.
professor,
Devashish
Dr.
De, to
Devashish
take
Dey,
over
to
the
take
mic
over the
for the
mic
program
for the
minutes.
program minutes.
Dr. Wasim Arif, Secretary of IEEE COMSOC Kolkata chapter, is there in the venue. If you Thank you, need any
Thank
sir,
you, sir,
for your
for your
opening
opening
words and
words and
allow
allow
us
us
to
to
proceed
proceed
ahead.
ahead.
Very good morning,
Finally, now I would like to
and
request our esteemed professor,
thanks
Dr.
to all the
Devashish De, to take over
participants,
the mic for the
offline
program
and
minutes.
online. And today we have two speakers, as everybody mentioned. That first talk will be Professor Chiranjib Bhattacharyya, Department of Computer Science and Automation. Good morning, at IISc Bangalore.
Now I would like
He
to
is already
request
present
our
and
esteemed
see online.
professor, Dr.
And his talk
Devashish
will
De, to
be
take over the mic for the
recent
program
advances
minutes.
in pruning deep networks. After that, we'll be hearing from Arif, Dr. Arif from NIT Silchar. He came all the way for this event. That how how to become member and all these things during the break time. And the next talk will be by Professor Shagatam Das. I think he's on the way towards the venue. And his talk is very interestingly demystifying generative large language models, a statistical perspective. So we are waiting for these exciting talks. As already everyone mentioned that ChatGPT is creating a lot of positive and negative vibes. Especially I can share you that I received a mail while I was editing a book in Splendor. The editors mentioned that that students have a habit, not students, like authors have a habit to writing papers nowadays using these models. I have to be careful. I don't know how we'll be careful. How I can take care of this, this language, this model to identify who has written originally and who has written by using this AI tool. So I believe that today's two talks by the expert will help us, even me also, to understand how it works and how to get rid of it. And how it is a, that every technology is a bad and good side. So how to use it positively for our society. Thank you. by the expert will help us. Even
Thank you, sir, for your informative and exhorting
how
words.
it works and how to get rid of it.
Now, the presence of such esteemed personalities will undoubtedly enrich our event and contribute to meaningful discussions and fruitful interactions. With immense pleasure, we would like to now introduce our first speaker of the day. We are honored to have with us today Professor Chiranjib Bhattacharyya, a distinguished expert in machine learning and the chair of the Department of Computer Science and Automation at the Indian Institute of Science in Bangalore. Professor Bhattacharya's research focuses on the foundation of machine learning, optimization, and their practical application to the industrial problems. His contribution to this field have been recognized with numerous publications in leading journals and conferences, including several best part of the paper authors. Okay. With a postdoctoral fellowship at UC Berkeley, PhD from IESc from Bhattacharya, Professor Bhattacharya brings extensive knowledge and expertise to his field. His exceptional achievements and research outcomes have made a significant impact on the field of machine learning. Today, we have privilege of hearing from Professor Bhattacharya as we present on the topic of recent advances in cloning deep networks. This talk promises to provide valuable insight in just a achievements and research outcomes have made a significant impact on the field of machine learning. Today, we have privilege of hearing
Good
from
morning.
Professor
Can you hear
Bhattacharya
me?
as we present. Yes, sir. I can
Okay.
hear you.
Yeah. So okay. So let me share my screen.
This talk promises to provide valuable insight
Share screen. Allow to share screen. Uh, can you see the slides now? Good morning. Can you hear me?
Yes, sir.
Okay.
I think now,
Yeah. So okay. So let me now share my
Not
screen.
yet. Yes.
now, yes, sir.
Share
Yes, sir.
screen.
It's
Allow to
visible.
share screen. Visible, right? In a slideshow mode, right?
Yeah, yeah.
Okay. Thank you. Can you see the so slides now? First of all, apologies for not being there in person. Um, I would love to be there, but because of various reasons, I could not be there.
Now, yes, sir.
Uh,
Yes, sir. It's visible.
so, visible, right? In a slideshow mode, right? So this talk is, I would say, not directly related. As I was hearing the introductory comments, so this talk, I would say, is not directly related to educating on the uses and applications of ChatGPT, but it is more, I would say, focused on some of the challenges in the practice of ChatGPT, I would say. So one of the practice. So today we are going to shine a light on uh, 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 one of the, I would say, challenges in widespread adoption of ChatGPT, and that brings us to a topic which is known as network compression, and we have some new results in model compression. So, and that sets up the title of the talk, pruning of deep networks. So I'm going to explain it the as the session goes. Uh, so I would like see. Unfortunately, I cannot see the chat window because it's Google Meet only allows you to share the whole screen. So if you have any questions, I would request the organizer to kindly stop me and you can relay the question. I mean, it's absolutely okay to stop me and ask any questions if you like. All right?
Yes, sir.
Okay, fine. So
Yes.
let's get started then. Let's get started.
Yes, sir.
Okay. So now, so I think a bit of a perspective is needed on why. So ChatGPT, right? So more than ChatGPT, there's this other word which is used called AI.
Yes, sir.
So you need to understand what AI is and ChatGPT is. To that end, a bit of a perspective, you know. So this leads to a very interesting philosophical question, which was posed almost 100 years ago. Like, can machines think, right? Now, this is a complicated question. And then one of the very interesting insights came from Alan Turing. I mean, I'm sure most of you may have seen this movie called Imitation Game. So there using this game, he provided a test. So, so he said that let's forget how machines can think, but let's say if a machine can, so uh, if a machine can fool a human being in thinking that's like it has human-like abilities, that should be we can deem the machine intelligent. In other words, this is based on a parlor game called imitation game, where there is a room, and let's say there's two rooms. In one room there is a man, and another room there's a woman, and there is an interrogator who is outside the room, outside the two rooms, and the interrogator does not know in which room there's a man and which room there's a woman. So the interrogator can only exchange questions in a piece of paper, and they can receive answers. Now, based on the answers, the interrogator has to say in which room there is a man and which room there's a woman. And the game is that they'll try to fool the interrogator. So, to that, motivated by that, they formulated the famous Turing test. It is that there's one room there's a computer, and another room there is a human being, and so the judge, let's say that's the person C, you know, exchanges questions, and if the judge feels that it cannot distinguish in which room there's a computer and which room there is a human being, the computer can said that is as intelligent as that human being, right? So this being the basis. So ChatGPT is that when I ask a question to ChatGPT, it responds to me with an answer, and say the answer is almost like human being, right? So that's why this field has gone like this. So now today, especially in the last 15, 20 years, there has been explosion of AI capabilities. This has come about because of many advances. So why not 50 years ago? Of course, there is many theoretical advances, but that was not enough to see the engineering realization of such things. So the advent of GPUs and advances in programming, of course, theoretically machine learning optimization, all this has taken us. Like for example, today you have human-like vision. So this is the like a pictorial image of the imaginary data set. And now on this data set, machines have almost human-like accuracy. We also have machines on our phones like Alexa and Siri, who are with whom we can converse. That is, they can understand and can give responses, almost like human like, right? So that basically this has given the feel that we are living in the age of AI. So how is this brought about? As we said, right? Apart from GPUs, this other interesting. So these GPUs have enabled uh, practical use of, or more widespread use of deep neural networks, so DNNs for short. Now, I've taken, and the power is there for us to see. The fact that IEEE Kolkata chapter is today discussing ChatGPT means that the power of AI has reached everywhere and is becoming topical. It's very powerful. Now, to make the subject a little light, the famous Spider-Man dialogue, right? With great power comes great responsibility. As some of our colleagues are saying that we should also think about ethics, fairness, and other things. Yes, it's important. And those are all important challenges. But in this talk, I'm going to shine a light not on those issues, but something else. So the fact is that we see ImageNet, we see this is this cartoon of a pre-trained transformer, right, which goes on to power ChatGPT, which comes out of OpenAI. All this is there, right, and it also brings in the issue of, as I said earlier, fairness, ethics, uh, and all kinds of other complicated issues while dealing with social life. But to me, the more important point is that what is the cost of all this? Just engineering costs, right? So one of the things I'm interested in is solving engineering problems, which are in industry. So if I ask, what is the cost of all of these, right? Can all of us, can each of us have our own chat GPTs? So if you start thinking about this, so one of the things I see is, so this great power comes with a great number of parameters, which is often called over parameterization, right? Now this brings in significant other challenges. So let us see what are the challenges. So now, again, a bit of a history. So in 1950s, people were started playing with these neural networks. At that day and age, in a laboratory, like 10 neurons were, like 10 units were experimented on, and the famous positron algorithm was invented, and the progress was slow. It took almost 30 years later, we could have something like 20,000 neurons, and it was able to at least do some speech interface, human speech interface kind of things. Again, far removed from human-like abilities. And now we have industrial models, right, which show billion parameters, and it is steadily growing. Now here, human speech interface kind of thing. So we have ChatGPT and all that, right? So now just to be clear, let's see, ChatGPT has like 175 billion parameters, right? So this is it's a large, so the power is coming. One of the reasons why the power is coming is because it has large number of parameters, and large parameters means it has ability to fit complex models, and because of excellent engineering, the complex models have been used to do useful tasks like answering questions and things like that. That's one view of the things, right? Now, but the question is again, what should be on our head is that at what cost? And this neural network, so-called neural networks, right? It has been inspired by how our brain works. So it's inevitable at this point to compare ourselves, the ChatGPT, with human brain, right? Now, so one way to think about it is, so what are the parameters in human brain? So, I mean, at a neurobiological level, uh, a grossly simplified version is that maybe you can associate. It's thought that the more the connections the human brain has, or you can say it's more complex it is. Right? So taking the simplified view, it would be good to compare the number of parameters with the number of connections the human brain has. Now you see a human brain has 100 billion connections. So you see this, and human brain can do much more than answering questions. So clearly, and it does at a fraction of is not as expensive as uh, ChatGPT is. So somewhere it requires new theories and new ways of doing things. So, but that's a different discussion, the new ways of doing things. But at this point, we now know that the ChatGPT, though, is doing a remarkable thing, but probably it's far from human-like. But now let's come back to the question of at what cost, right? Now, what is alarming now in today's day and age is what we will call as the carbon footprint of AI models. Right. Now, I would like to draw your attention to the third column, which is carbon footprint, right? So it's pounds of CO2 E. So E means equivalent. So this is a notation that is that your carbon footprint, that is energy consumption which you do, is what is the equivalent CO2 emissions. So it's called CO2E, right? And now on the first column, you see this BERT, Elmo, GPT-2, transformer, shared architecture and things like that, right? Now you see these are pretty small models compared to GPT-3, but you can already see the alarming energy levels. So I say energy levels, I would again, so let's say this measurements are there. Now this measurement in the first row, the measurement is, as reported, is the energy consumption in one iteration of BERT. BERT is, as you know, a kind of transformer. So it says the energy consumption is something like 1,438 pounds of CO2. Um, for example, if you have transformers, which is like 213 million parameters, right, with the neural architecture search NAS, you can see the carbon footprint is something like 6,26,000 an hour. For example, if you have transformers, which is like, now we need to put this in numbers perspective. How high is this number? That is high, it's low. How do we know? Right. So now to put this in perspective, you know, so now it is now estimated. I mean, these are other numbers from other figures, right? So air travel between New York and San Francisco, right, on a single passenger, the equivalent carbon emission, right, is something like 1984. Now you see that is roughly one iteration of a BERT algorithm. A lifetime of a car, it's this is all US based numbers, right? Is 1,26,000 CO2. Now, if you go back to the row on transformers, right? It's like 6,26,000. It's almost 5 times. So as you can see, this is quite alarming. Alarming because if you look at any, say, for example, if you track research papers, right? Forget industrial application. Track research papers. For any research paper who wants to adopt BERT, you want us to uh, train the BERT model many times, right? Now you can see almost, so the carbon footprint is almost very high, like, flying from New York to San Francisco again and again. So more of this you can read in this very interesting paper who first pointed this out in Energy and Policy Conservation Including NLP. And this actually has made the field take note and sit up. So continuing on the same thing, because you're talking about GPT here, so there is this follow-up study. I'm sorry, it should be 21. Patterson came on 21. So you can see the number of parameters, as I said, in GPT-3. So concentrate on the last column, like 175 billion parameters, right? Now, so so if you really want to model that, now, so it says that take, I mean, forget training time and all that. That's well, like, that we can come back later. But the point is, if it is second last row, the net TCO2e. CO2e already we talked about is the equivalent carbon dioxide emission, and T is tons. So the net tons of carbon dioxide emission for training a model is something like 552. And just to put things in perspective again, this is equivalent to 3 times the carbon footprint of a jet plane flying between San Francisco to New York. Now, clearly, you see, you can read more about it in this paper, and so clearly, this is absolutely not possible, and that's why you will see there are several people around the globe saying that at this point maybe this is not a sustainable thing to develop. Because once you have seen the power of ChatGPT, and it's very rational and important that all of us can have our own specialized versions of it, but the energy cost, the current the way it is, is absolutely. So this brings us to the research topic of the day. Um, so it is. So 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 the point is that how to reduce the carbon footprint of deep neural networks, right? And I've deliberately called it not transformers but deep neural networks to keep it general. Now, so one of the recommendations is that you have a smaller model. But if I make the model smaller, as we discussed, the model's ability to do interesting things will come down, right? Now here lies the challenge, right? I can reduce the model, but it should be able to quantize and distill, like it should have the same modeling power, right? Though the size is small, right? The way to go about it, one can distill a smaller model. Distillation, those of you know, is a branch of deep neural network study where you try to build smaller models, but often these are becomes. This is a valid thing to do. Another is quantization. That is, you do not store the parameters with all the real values, but store it in, maybe a few reduced bits, and then use those bits to, and use the fact that stored in bits to, store up, is to speed up your arithmetic operations. So we take a different view. We say that we want to do pruning. So pruning is removing weights or connections, or reducing even structured subunits called filters. So this is our goal, and we have some new results to present. So just to get you a quick preview of what pruning is, and say pruning, oh, okay, we know this. So basically, it's a principle of parsimony, right? That is, use as less number of parameters as possible, and then one could see that if you can fit the model to the data which you have. For example, the classical problem of best subset regression. That is, you want to figure out from a d-dimension data what are the right features to do. And for example, you want to solve a least squares problem where you have a response variable capital Y, all right, and there are n such variables. Then, sorry, there are n such data points and d variables. So what you do is you try to say that, okay, give me the least number of features which is enough to model the data. And now one can say that give me a model which is like which is at most k elements, right? And this is sometimes called the zero norm and all that. So these are NP hard, but one can approximate that by lasso and things like that, right? They're not easy problems, but again, we know in the last 15-20 years there are a lot of study on this, so we can borrow some of this. Now in the ChatGPT style thing, if you want to take the same thing, is one can formulate the problem something like this: that look, if a pretend model has W0 as number of the parameters, then can you find the lowest number of parameters such that the loss, and let's say the loss, so f of W0 can be the loss function. So the loss is almost at most epsilon times, right? So it almost epsilon times the accuracy drop, right? And f of W is probably the new loss. Now, one would like to solve problems of this kind, right? Now, as you see, the constraints and objectives have been different. F is no longer convex and all kinds of things. So the lasso kind of setup will not particularly do. So to that end, one has given the field of pruning deep networks have arisen. So think like this. At this point, this is a cartoon of a deep network. So each block is like one of the filters, if you know what I mean. So now, in unstructured pruning, what we do is, we remove any weights which we want to. And so now these have been drawn by white boxes. So if this white box means it is removed. Now, unfortunately, if you do like this, and here maybe direct application of things we talked about earlier may work well, but at least statistically, but is very difficult in an engineering perspective. It often does not give you the same efficient speed up in terms of flops and doesn't translate into energy saving directly. So there's a growing realization that we should do structured pruning. And now, so now there is this realization that structured pruning is what gives us reduced inference time. And inference time means, I present you with a picture of an image, a picture of a dog, and say you have to correctly say it's a dog or a cat, and things like that. This inference. Now the inference time is low, the power is also low. Right, and that brings us energy level. So unstructured pruning often does not do these things. So now, so current practices in structured pruning is, it is a pretty well studied problem. It's there around 30 years now. however, but some of the approaches are not really that while it's there, but may not be as effective as it should be because of this large number of the sheer size of the neural networks which is currently in operation. So people sometimes directly try to throw away, for example, the weights whose magnitude is low, or sometimes say that the gradient values, that is, gradient respect to the loss function, right? It's those magnitudes, relative magnitudes are not high. You can say that okay, that dimension can be ignored. Uh, uh, or maybe somebody would want to say that okay, we want to find out the least number of to mimic the least square angle, right? So someone say that okay, if it can reconstruct the L plus one layer, the output, uh, we should be happy about this. Now, one of the things is we are seeing is that these models, like for example, it is not physically possible to retrain the models with the exact same data set. Number one, and number two, is often the data set itself may not be able to be shared or may not be available when I want to retrain it for something. For example, like if I want to do GPT-3 and want to, you know, try to see if we can make it smaller for my own practical or for my own use, right? I may not have the same data set. So the access to the same training data remains a challenge, right? So to this end, there is this growing realization that that probably we need to look at other areas or think about ways to do pruning without access to the same training data set. So this is sometimes called data-free pruning. A caveat is data-free pruning doesn't mean it doesn't require data. It's only saying that the data set on which you have used to train the original network, that doesn't require data. Now, and of course, this, as I was alluded to, so this is unable to like privacy and security and all kinds of other things. So now this kind of research where I don't have access to the training data, data-free pruning. In unstructured pruning, there is some work, it's a beginning work, a new area of research. But structured pruning without data is still under researched, and this is the gap we are currently engaged in filling. And someday, hopefully, that will really help us reach the GPT-3 kind of situations. So the main idea which I wanted to say now, I see I'm hopelessly out of time. So on two papers, which just got published in ICLR this year, and there are the students. So the bottom left are the two students, the two and Chaitanya and Tanay, and the other two people I think were other attendees at ICLR this year, which has happened in Kigali, Rwanda. So so what I will do is initially, okay. So anyway, started 15 minutes late, so I can be here till 10:15. I'm sorry about this. So maybe what I'll do is we'll quickly run you through the basic idea of distributional training and give you a flavor of the second work, which is pruning coupled connection. This is more close to transformer kind of models. So what I will do is so the fact is that as we know that we don't have access to the original training data, right? Now we make the following assumption that I don't have access to the training data. That is, suppose, what you have told me, here's a network, pre-trained network. You said that, okay, can you prune it? By pruning, as we know, is that can you remove some of the weights or structured connections so that my loss function, is my accuracies are not significantly hampered, but but the number of parameters are substantially lower. So now, since you told me the task, that task is again, let us say, to distinguish between cats and dogs, right? Now I'll say that you don't give me the same training set, right? But let's assume I have a distributional access. In simple words, by distributional access, we mean that okay, I know finally you would hold me to distinguish between cats and dogs. That I know, right? So nothing stops me from going and shooting images of cats and dogs, right? So that's what we call as a distributional access to data. That's the way you solve it. So now, as you said, right, I alluded to that I have distributional access to data, so that exact training data or the loss function I may not know, right? But I know it's a reasonably well-trained network. which does a very good job in distinguishing between cats and dogs. So what I'll do is I'll go and shoot some pictures of cats and dogs, which may not be there in your same training set. That doesn't matter. And then using that, I can also do the following. I can also see how each of the units which I wanted to remove. So units can be a weight or a filter or any of this, right? Um, and I can measure all these things. Now once we do that, uh, uh, so then we introduce a new idea called discriminative filters. So this is more like the classical discriminant analysis kind of idea here. So what we say is that if a filter, you know, reacts differently to the different classes. For example, the top filter, right? Let's say the yellow curve is for the dogs and the blue curve is for the cats. So that is, you feed in all possible images of cats, and that's the response profile. The blue is the response profile which you see, the output of that filter. And when you respond to, and the yellow is one for the dogs. So you see, but so there's a marked difference between how it responds to the cats and the dogs. But the bottom one, roughly responds the same way, right? So I'll say that the top filter is more discriminative in some sense, right? Than the green filter. So now, if I want to, so the high-level idea is that now if I want to remove something, maybe if I remove the green filter, right, I will not lose much in terms of discriminating ability, right? So this is what it is, right? So we go ahead and posit an hypothesis that most networks will have, well-trained network will have discriminative filters. Now that's not entirely true, because at the initial layers, there is filters which are not at all discriminative, but trying to discuss, trying to generate interesting features, right? So maybe well-trained methods have a mix of discriminative and non-discriminative filters, and then we say that okay, and what is useful for generalization is discriminative filters are the ones which probably gives you better generalization. That is better classification accuracy, and stands in the with good features, right? So now, can you verify this? Of course, we in the paper, if you dig up, you will see some results to that end, that we see indeed this hypothesis is true, and then that sets up our work for distributional pruning. So first thing is that now if you say that the first question that will arise in your mind is, oh, okay, you said discriminative filters is the thing is true, but how will you test it? How will you find out what is a discriminative filter and questions like that, right? So now, so apart from identifying what is a discriminative filter, we need to see that, so first thing is, now if you can it help identify hard to prune layers, right? So for example, in the initial layers, there is very little discriminative layers. So now it's only for developing good features, right? So all layers, so just because things are not discriminative doesn't mean it is not useful. So now can we identify which layers to prune, how much to prune, and things like that, and now can devise a suitable algorithm and then demonstrate the algorithm works and things like that. So now how do you first go about it, right? Now to just to make the thing a little bit lighter, those of you who are a fan of Calvin Hobbes, probably may have come across this interesting episode where Calvin is, even after seeing a great sunset, is saying, "I'm missing the great TV shows." So TV. So what is TV here? Of course, it's not television. So TV is sometimes called the total variation distance, sometimes called statistical distance. So we take hold of this. So essentially, a short summary is that between two distributions, the TV distance, the statistical distance between the two distributions, is basically the maximum difference in probabilities on a single event, right? So now, so this is widely useful in comparing various kinds of distributions. Of course, there are other measures as well, right? Now, so use this to identify discriminative versus non-discriminative filters, right? And now, I mean, of course, this is a very complicated quantity. Closed form expressions are often not available unless they are very simple distributions. Gaussian is a very ubiquitous distribution, and sometimes bounds are available for Gaussian distributions. Now, since I thought it's IEEE Kolkata chapter, so I thought we will bring to bear the famous Bhattacharyya distance. This was invented in 1930s. Gaussian is a very ubiquitous distribution in Kolkata itself. So the one is the Bhattacharya coefficient, where so if small px and small qx are the corresponding densities, right? And if it is a discrete distribution, you can think about it as corresponding um, um, PMFs. The BC of the coefficient is defined as this. This is also called the affinity. Now, the distance is, the minus logarithm of that, right? So now, so fortunately, for Gaussian distributions, coefficient is defined as this. The Bhattacharya distance is a very nice closed form expression. And now that can be leveraged to get a bound on the statistical distance through, again, a variety of relationships. It is for Gaussian distributions, this one is called Hellinger distance. I'm sorry, there should be a square on this root px minus root px square. Right. So Hellinger distance is essentially 1 minus the Bhattacharya coefficient, between the two distances. And actually, Hellinger is actually the Hellinger square is the lower bound on the statistical distance. Now you see, if you can put all of these things together, you can easily find a like a lower bound on the statistical distance between P and Q, if P and Q are Gaussian distributed. Right? And that we are going to use it later. So now what we do is, now we take each filter, and suppose there are k classes, dogs, cats, monkeys, and what have you. So we compare the minimum pairwise the TV distance, right? Now, and say that the minimum pairwise TV distance is high. We can say that, okay, this is probably a discriminative filter, and that's the idea, right? So now, and the sufficient condition is that if the lower bound is between the distances well separated, that also can be considered as a good proxy. And for the lower bound, we use the Hellinger distance, right? And that's essentially the idea. This is rewriting the same thing as we talked about. So and now, since this is not easily computable, the main key insight is I can use Hellinger to compute a lower bound and go from there. Since I'm rushing out of time, so I'll just quickly do this. So as I said, that the final formula, when we assume that the filter-wise class conditionals are Gaussian, spherical Gaussians, can be written like this, right? So using this formula now the mu1, mu2, sigma 1, sigma 2, right? All this now can be easily, sort of computed from the distributional axis. That is the data, not the training set, but the data which we generate, right? Now I will not have the time to go into this in some detail, but the essential idea is that I can now, using the previous setup, I can identify what discriminative filters are, and try to get a heuristic, try to get a like a fraction of, for every layer, I can get a fraction of the discriminative versus non-discriminative layer filters. Let's call that tau. Now, if tau is like 0, that is the number of discriminative filters is 0, does not mean the the layer is not important. Maybe it's good. Maybe it's helping in developing good features. And if everything is discriminative filtered, that's also not very good, because at least empirically it is seen that that means I mean, we have seen empirically also that if you keep all of that, that also does not give us too much saving, right? So, but what we found is, of course, this is an heuristic as of today. That's what I proposed. That 4 tau into 1 minus tau. So you can see this number is between. So that number is a very useful metric to prune, right? So. Uh, and now here is our results, if I may say. So it is our results. So the TVS prune is our pruning algorithm, which is based on TV distance and hence the TVS prune thing, right? And you can see and now here is our results, if I may say. The accuracy drops, right? Our accuracy drop is probably much more minimal than some of the state-of-the-art methods on the so the first one is on ResNet and the second one is CFAR10, and these are for different values of the parameter sparsity levels. Right. So the interesting thing is, so on the graphs you see on top, right? Now, so chip, for example, is a state-of-the-art method. Now, we could beat chip, but chip requires access to the exact training data and the loss function. So we are not doing any of this. Without having access to all of that, we can easily beat chip. And but what a very interesting realization is that we can easily reduce if you so for example, take the blue curve on this three diagrams, right? We can easily reduce the accuracy number of parameters by at least 30 to 40% with hardly any drop in accuracy using the discriminative filter hypothesis, right? So this shows the level of over parameterization, and hopefully this will give us much smaller models and which could have much better energy footprint. And now, so now, so interesting. So now let's quickly switching gears to this other idea that see this just removing parameters, right? May not give me the savings in power, because saving is power is actually dependent on the latency, right? And how, so the point is that the same parameterization, so in instance removed networks, I must engineer it well, right? And that requires careful coding and things like that. So one of the things is that to see the same inference time gains, right? One has to track a little bit more closely how the neurons are situated in the kinds of neurons, and especially in the modern deep networks, for example, transformers. There is something called coupled connections. So these are much more difficult to prune, and what we find in existing pruning algorithms, and most algorithms avoid pruning these coupled elements. You know, for example, what we could measure, and that's more there in the paper which I showed you. So you could see ResNet 50, almost two-thirds of the time, these connections consume more than 66% of the inference time. So that means these things, if possible, should be pruned. But unfortunately, it's not very easy to prune them, and definitely very complicated in the data-free regime, right? So we took a crack at this problem. These connections consume more than is so now existing approach of pruning networks is that you prune in a layer-wise manner. That is, and you assume the following, that if the subsequent layers are will not pruning one layer will not going to impact my inference time in a layer before. Now, in a coupled connection, this may not be true, especially for example the skip connections, right? That is, that if you remove something here, it can go back and have an effect on the previous layer itself, right? And the another thing is that here saliency, the way, saliency is something like the relative importance of whether you want to keep a network or not. For example, the way we thought about distributive filters, right? Uh, it does not depend on a single neuron. It depends on which other neurons you're also removing. So this coupled connections has this other problem. So to get some of that, right? And now all these questions have not been studied. So I mean, so just to give you an idea that so this coupled connection, for example, the pink thing on top, right, is connected to the you know so layer 12, 13, and 14. So there is a skip connection through layer 15, right? This comes to that, right? So now, so now if I remove these classes, it will also have an effect on the ping connection as well, right? In the 12th thing. So the idea is to track the data flow more efficiently. And now student and I found out a very nice way to do that, and you could project it like a graph or dependency graph of sorts. And this graph now tells us how data is flowing. And based on that, one can now design some sort of a saliency score. I mean, so at this point, probably I don't have time to get into go through all of these. But we but the idea is that here it helps us because depending on the graph, one can then come up with a saliency score to say if you remove this, which other neurons would be affected, and one can accumulate some sort of scores towards that, right? So long story short, after all this, so basically you from the data flow graph, you compute saliency over this, right? And then and of course, accuracy. If maintaining accuracy on a test set is concerned, that we do. But what we really want to do is to see that how much speed up I can get on my GPUs and CPUs, and that's where the real challenge is, right? Now, as you can see here, right, the DFPC is the algorithm which we proposed. So the CPU speed up is significantly much more, and that's where the CPU speed up directly is related to energy consumption, right? So 2020, so you can see here, the savings can be as high as 30 to 40%, and in some cases, for example, can be double. So these are the so I mean, of course, this is on a small set. It's on CFR 10, but this is just to prototype. This is just to get the point across that. So these kind of research is going to be useful in arriving and lowering the energy footprint. And if you don't lower the energy footprint, the ubiquitous use of GPT would not be possible. So with that, let me close. This is 10:15 already, and I have to leave now. And you're welcome to check out our code. It's here in this website. So again, thanks for listening. It was a pleasure talking. I'll be happy to take a couple of questions. You know, you're welcome to check out. Yeah,
For
so
this
that's
introductory
here
lecture.
in this website. If there are any, so again, yeah. Thanks for listening. It was a
Thank
pleasure
you,
talking.
sir, for this intriguing lecture. There is no doubt the topic is going to be really lucrative for our future. May we kindly request your permission to take up some questions for the audience?
Sure, sure. Most welcome.
Okay, sir. So if anyone has any questions, please raise your hands in the audience, and online participant can raise hands in Gmeet. They will be given the mic access, and also you can ask through the chat box. Okay, there is a question at the seat. Give him the mic. So if anyone has any questions, please raise your hands in the audience, and online participant can raise hands in Gmail. They will be given the mic access, and also you can ask through the chat box. Okay, there is a question
Hello.
at the seat. Give him the mic.
Hello.
Hello.
Can you hear me, sir?
Hello.
Hello, can you hear me, sir?
Yes, yes, I can. I can.
Morning, that's a nice talk, sir. I have just one question. I am Ori Chakraborty. Sir, the learning rate of the deep neural network, does it have any impact on the carbon footprints or CO2 equivalent?
Yes, yes, I can. I'm sorry, I didn't could follow. I think is your question is the learning rate has an impact on what?
Yeah, yeah, yes, yes, exactly.
Learning rate on impact on what?
On the carbon footprints equivalent CO2.
Uh, So see, I mean, so that maybe one has to go into those other papers which they actually measured it. So the idea is that if you use more time to train, right, and obviously you're going to spend more energy. So in that sense, it has. But I would point you to the papers I mentioned. There, those things may have been discussed.
But there are some data sets.
Huh?
I have limited experience in this particular domain,
Hmm.
but from my limited experience, what I can see that even if the learning rate is set to max,
Hmm.
and even if for some data set,
Hmm.
the time, the CPU time, I mean, the number of iterations we do or the number of computation we do will significantly increase the CO2. That's what I understand from this nice talk. But for certain data set, even if it's set the learning rate to max, execution time is still not. I mean, it's not that I mean, in
Yeah.
total.
So just to be clear. So see, this is an instance of a non-convex function interacting a very complicated architecture on various data sets. So it depends on the starting point, depends on data set, all kinds of things, right? But so what as energy is concerned, right? So the more time you spend the network, the more energy you're burning, right? So anything which so now so one simple strategy, right, is set the learning rate to the maximum and I'll get good result. That may be disaster because it depends on the initial condition and was the local minimum wherever it is kept there, right? So there are, I mean, so there are no good theories for, at least in this setup. It still largely remains empirical. But so far, again, I'm repeating, so far, again, this discussion is concerned, the energy footprint of deep networks and their impact on learning rate may be best discussed in the references which I was alluding to.
Actually, sir, I am asking this so because I
Huh.
have seen when I use the say vector quantification like LBQ, ONS, and then when I apply this thing on the non-redundant reduced data set, I have seen fast result. Maybe that's not a conclusion, but for my personal experience, I have seen that the feature optimization using a proper algorithm, I think it may help.
Yes.
From
Yes.
my personal experience.
Yes. Yes. So, is there any other question? Yeah.
Thank you.
Right.
Thank you, sir.
Uh,
There is a question on the chat box.
uh,
So Shuman Shahvi, this prone can be used on transformer.
no, TVS prune is yet to be. So as we say, this to do, we have to still merge it with that. So to still know how to do coupled connections and things like that, right? So we are still in the process of doing all of that. So so maybe coupled connections, the second algorithm, and the first algorithm that we should do. And of course, one can today use it, but it won't be that effective.
So, I'm Professor Itisha Misra. It is Dr. Bhattacharya. It is a wonderful explanation of your research work. Generally, we do not know the perspective of the mathematical formulation on ChatGPT. So, researchers should be more, should have more attraction on this thing, how we make the carbon footprint lower down, how we can lower down the carbon footprint. But my question is related to this thing. From your lectures, what I got, the 175 billion parameters are there for the chat GPT that requires almost 1287 megawatt of hours and 552 tons of CO2 emission. My question is that for any particular solution using chat GPT, is it not dependent on the problem solution? It is, there will be a variation of the carbon footprint from problem to problem to get solution using chat GPT. Is it so?
See, the number which is reported is training the chat GPT, right? Now the
Okay.
point is point is that the way they train it. See, see, this is industry scale. So industry scale is you treat everything up in the web, whatever you can collect, use it to train.
Okay, okay, okay,
So
okay.
that is why you can ask any question on it. You can ask, write poetry, you can ask, write chemistry, you can write history, geography. How's it doing it? So it treats all the whatever is there in the web as a data set. Now
Okay.
this kind of engineering challenge, so hence it will not change too much. I'm saying, given that that's the
Okay, so this we can think it 552 tons is the average CO2
yeah.
or expected for every problem.
And, so now the training of ChatGPT is over all even everything on the web, right? So data
Okay,
set roughly is the same, isn't it?
okay, okay, okay. Thank you.
Right.
My question is that basically in case of transformer footprint, what are the measures, what are the steps we can take for the reduction of CO2 emissions?
Exactly. So now the currently see now. So one very vanilla thing which you can
My
do in
question
our
is that
labs, right,
basically in case of
is to first,
transformer footprint,
can I do the same task
what
within
are
less
the
number of
measures, what are
parameters?
the
Number one,
steps we can
that's what I'm
take
trying
for
to
the
aim at
reduction
for,
of
right?
CO2 emissions?
But
Yeah.
that's also not very useful. That's also not, you know, more effective to save energy, because those of you know energy, so energy is very standard electrical engineering, power into time, right? So that means unless I have working code which translates into less time, the time I see, right? So the network is working, right? So it's also the engineering factor must also come in. Now to do now often it is now given in the pruning literature, because as you can see this is very important. You talk to industry colleagues, they'll say, oh, because they reduce number of parameters, don't think your time is less, because I have to do engineering wise also, right? So that is why what do we, and the lots of other things, for example, couple connections, skip connections, and things like that, right? Now, unless we address them as well, we may not see the gain in time per se. So in our laboratories, where we don't need industry grade things, if you can come up with careful measurement of, the inference time. Inference time means I give you one image and tell me how quickly, and tell me it's a cat and dog, right? If you can measure these inference times and show that actually, it is lower, and how much lower, if you can measure all of these things, that can be good proxies. Now measuring the directly carbon footprint and all that requires much more infrastructure, which often even IISc also we don't have. So that's maybe even in Google and things like that, that's possible. But probably in laboratory setup, it may be difficult to do these measurements. But having said that, I would point to the first paper I mentioned, right? The Struble paper in 2019. So where they did it from UMass, so you can see, we can get some ideas from there as well. This would be my response to your question, right? What can we do? Sort of.
Yeah, basically the transformer on the basis of the structure and on the function of the transformer, what are the parameters we have to focus to reduce the CO2?
As I said, right, CO2 transforms many parameters, right? Now,
Yeah.
what you can do is you can measure. So one experiment you can do is, you give in a
Yeah,
query and
basically
see how
the
much time
transformer on the
the
basis of
transformer
the
takes to
structure
process the
and on
query, right?
the
So
function
this
of
is
the
one.
transformer, what are
This
the
is a baseline.
parameters we have to
Now you
focus
say
to
that,
reduce the
can I
CO2?
remove some neurons? Can I remove? Can I do things
Yeah.
differently so that the query, the time processing the same query comes down dramatically? Number one. Number two is, the query must also be answered correctly. No, if I start removing things from transformer, right? Probably the model complexity would go down, and hence it may not be able to solve the query, address the query appropriately, right? So, these two things has to be factored. And now, as I said, you can focus on then among the things which you can do to the transformer is remove elements, structures, for example, filters and things like that. Number one. Number two is, you can also see that do some engineering, like the things we're trying to do, like couple channels and things like that, to see that the time to process the query also comes down.
Okay, sir. Thank you.
Right.
Thank you, sir.
Thank you. So, so my apologies again. I couldn't be there. It was a pleasure talking. So at this point, I'll take my leave if you don't mind. There are other pressing things.
Resuming from the previous session, hello everyone, Shankar Pramanik here, and I will be your host for the rest of the day. Now we are thrilled to hear from Professor Dr. Swagatam Das, who is a distinguished researcher in LE with expertise in control engineering. He holds a PhD from Jadavpur University, India. As a professor at the Indian Statistical Institute, Kolkata, he has published over 400 research articles in renowned journals and conferences. He is a founding co-editor-in-chief of SWAR and Evolutionary Computation and has served as an associate co-editor-in-chief for prestigious publications. He has received accolades including the Young Engineer Award from INA. He is an integral part of the machine learning research group, which has achieved notable success, accepted papers at ICML 2023, AI Stats 2023, Triple AI 2023, and IEEE CBPR 2022. His expertise and impactful research have established him as a prominent figure in this field. So let us all welcome Professor Dr. Swagatam Das on stage. And IEEE CBPR 2022. His expertise and impactful research have established him as a prominent figure in this field. So let us all welcome Professor Dr. Swagatam Das on stage.
Flower bouquet তো দিলি না।
And impactful research have established him as a prominent figure in this field. So let us all welcome Professor Dr. Swagatam Das on stage.
ফ্লাওয়ার বুকে তো দিলি না। এটা পিন কর। ঠিক আছে, স্যারকে শুধু পিন করো, বাকিগুলো ইয়ে করো। চ্যাটটাকে সরিয়ে দে। এরকম থাকবে? হ্যাঁ থাকবে। ঠিক আছে, স্যারকে শুধু পিন করো, বাকিগুলো ইয়ে করো। চ্যাটটাকে সরিয়ে দে। এরকম থাকবে? হ্যাঁ থাকবে।
Okay, so
এটা
good morning to one and all, and with courtesy, I begin this by thanking the coveted organizers of this beautiful symposium, especially Professor Navamita Das from Indian Statistical Institute, or very own Navamita, for inviting me to this program. I hope this link is visible, but there might be a small problem of resolution because it is being mirrored from another Google window. So initially, I thought it's a new program, like some statistical perspectives on deep learning models and ChatGPT, which is an interface between human beings and the so-called large language models that are taking all the headlines by storm nowadays. Is an example of instantiation of such generative models on there. But then I added another phrase, ethical and digital perspectives, which is also very important. Am I audible to all of you, or you can compare? So, and if you look at this beginning slide, there is something written over there. I don't know whether you can read it or not. It says your machine learning can only be as good as your training data. We live in a world of data. If you look at this, all of us now have our digital identities. All of us means those who can afford the luxury of using smartphones, internet, etc. That means the netizens. And netizens matter a lot to the society nowadays, even much more than citizens, right? So you will see headlines like netizens are thinking this, that, about that film star. That actually is the rating to nearly in all professions. Really? So the data, that is the huge amount of data that is being generated all through. We have heard that this data is the new oil. And if data is the new oil, so the data, then machine learning systems are the new engines which feed on that oil, which drives based on that oil. But if the oil is not properly filtered, if it has precipitates and other impurities, then what will happen to your engine? Your engine will gradually start completely malfunction. Yes or no? So we will see that part in this critical area, which I would like to highlight and we will comment later. So, so your machine learning can only be as good as your training data. The data that you are feeding into your system. So now coming to this is a brief roadmap. We will, and of course, I will take the liberty of skipping many things. I don't want to bore you for next 2 hours or so. So we start with the concept of what deep generative models are for image data from a statistical point of view, probabilistic generative networks, then towards text and sequential data, recurrent neural architectures, large language models, and some category theoretic framework, just the initial outlines of a formal mathematical framework in model language, then bias, ethical violations, and dangers associated with LLMs that all of us should know when we are especially thinking of, at least many young people like you are thinking of doing machine learning practices in near future. You should be aware of the ethical violations associated with the systems and some future thoughts. This is the brief roadmap. Now, deep learning has been there since 1980s actually. It has rose to huge prominence since 2011 with the publication of one paper by Jeff Hinton and two of his students. One of these students who published that landmark paper in 2011, Newriggs, is also the CEO of OpenAI. We will later come to the name of that person. So the inference model, machine learning inference models are of two types in general. One is called discriminative or predictive model. It's a difficulty to resolve the slides. But anyway, if you look at it, there are two types of machine learning systems. In one system, you represent. Am I still audible?
Yes.
So one system you represent the objects in terms of their most suitable features. As we saw in some features, there are objects from two different classes. The machine learning system is very happy to learn a Lakshman Rekha or discriminative boundary between these two. This is what we do in common classification techniques. Even a straight line is a classifier. The straight line divides, partitions the R2 into two parts. On one side, if you plug in the coordinates or features of these points into this straight line equation or expression, it will give you positive sign or positive number. On that side, if you plug in, it will give a negative number. Very simple. So this, even this straight line is a classifier. In fact, every neuron in the neural network is a classifier. You want to have So, on the other hand, coming to generative models, let me tell you what is meant by data, by the way, before I go to the exact definition. Anything and everything around us, which could be abstractly represented, stored, processed, retrieved by a digital computer in terms of suitable numbers sitting together, qualify as data. So when I go to a bank and I open up an account in my name, I ask for a loan, I start being specified in terms of my fixed deposit amount, CIBIL score, credit rating, etc. A lot of numbers sitting together. Even the names, street address, these are also converted into arbitrary certain numbers and finally to bits and bytes. These set of numbers start specifying me, I become a piece of data. All of us are actually a piece of data. Okay? Some server or the other. These servers are accessed by Google, Yahoo, Facebook, eventually by the government, etc. Now the question is, this is one sort of definition. Data is an abstract representation of physical objects. Okay? And this abstraction means specifying the physical object in terms of certain numbers sitting together. You have a gas-filled container fitted with a piston, which all of you must have seen in physics. Now, this container is specified in terms of three numbers sitting together: pressure, volume, temperature. And this vector is its data identity. This is one definition. This definition is closer to computer scientists like you. But from statistical point of view, what is data? Statisticians believe everything, unlike common people like us who believe everything comes from nature or God. Statisticians believe everything comes from an internal random stochastic process. Every object is kind of instantiation of that internal random stochastic process. So certain random variables govern the current perception of that object. That object is an instantiation of a random process. So data is also, they believe data is some kind of observation or instantiation of a random process. If I say the amount of rain in Kolkata on July 3rd of every year, it's a random variable basically. Now, if somebody is observing this amount, somebody is recording this amount in 2022, 21, 20, 2019, etc. These values that they have recorded, these are the instantiation or specification of a random variable. Okay, specific instance of a random variable. Qualify as time series data. We don't know what will happen in 2024, 25, etc. So data, the data points that we have with us from any sector, from medical images, from financial transactions, all these data result from some underlying random variables. These random variables could be correlated, uncorrelated, univariate, that means a scalar value, multivariate, that means multiple random variables together. But their, instantiation is there. So here you see the generative models are not concerned with classifying the data cloud into two classes, etc. What they are concerned about is how to model this underlying probability distribution of the data. So now this problem is there in statistics for last 200 years. So what's so new about it? I give you, I don't know how many of you have heard of Gaussian distribution. All of you, right? Normal distribution, all of you have heard. I give you 10 random numbers, 2.8, 3.1, minus 5.6, 7.8, and so on. And I ask you, tell me the univariate Gaussian distribution, that means scalar Gaussian distribution, from which these numbers are most likely to be sampled. What would be your answer? You would immediately, if you are a student of statistics or even not, a student of data science maybe, you will immediately churn out the maximum likelihood estimation and tell me the mu and sigma of the Gaussian. It's a standard technique in statistical estimation theory. And statisticians with pen and paper prove that this technique is consistent, has very good properties, and blah, blah. But instead of 10, 20 scalar numbers, what if I give you 60,000 images, and each image is a handwritten digit from 0 to 9, 0, 1, 2, 3. How many of you have heard of the IISc data set? Many of you might have heard of the IISc handwritten character data, or digit data set. Or even not, it's a data set from multiple users who have written these numbers from 0 to 9. Each digit is packed in the form of a picture. That picture is 28 cross 28. 28 pixels by 28 pixels. So I give you 60,000 such 784 dimensional vectors, because 28 cross 28 is 784. Then I ask, approximate the probability distribution from where these images have resulted. Give me, this is also better. So give me the probability distribution from where these images have come. And that probability distribution should actually have, what is the shape of Gaussian? It looks like this. Now, this probability distribution you can think of as a 10-peak system in a multivariate space. If you imagine it for 2 dimensions, there should be 10 such peaks, okay, which are called modes. These peaks correspond to each of these 10 digits. 0, 1 peak for 0, 1 peak for 1, 1 peak for 2, and so on. This is exactly where generative models help us. So generative, in these generative models, these probability, it's a very complicated problem. 784 is nothing. Nowadays, every one of us has megapixel cameras. How many megapixel cameras each of you are carrying? Might be 28 megapixel or something. If you think of 1 megapixel image, 1000 pixels on this side, 1000 pixels on that side. So we have 10 power 6 raw pixels, right? Now these 10 power 6 raw pixels, if you flatten it, that means stack all of them in a vector, you have a 1 million dimensional vector. And on that vector, this vector is an instantiation of a 1 million dimensional or 1 million variate random variable. What is the underlying distribution of that variable? This is the very question. Can we approximate that distribution? Deep generative models use neural networks and a lot of heuristics to approximate this distribution because statistics has no answer for it. Okay? In fact, I have been telling this to the statisticians of Indian Statistical Institute in the StatMath department also. I gave a similar lecture, and they agreed that yes, beyond a certain dimension, if your number of variates is huge, then all NLE-like techniques become inconsistent, they break down theoretically. So then we only have the option of deep generative models or neural networks, which could model this distribution. And what is meant by modeling, I will come to that. But before that, so this is deep generative modeling. You have certain pictures. These pictures follow a certain distribution. This is PDX, if you cannot see. This is the data generating distribution, which we do not know for sure. We could only have some samples from this distribution. Then the deep generative model actually processes these samples to approximate a distribution with p theta x. That p theta x should be extremely close to the PDX. And if when that happens, what is the advantage of it? When this happens, we can actually sample from that approximated distribution. What does that mean? Sampling from the approximate distribution means you become like God. You can create artificial images, videos, text, whatnot, artificial speech signal, everything you can create because you are approximating the distribution from the samples. And then you can create it with such a realistic order that it becomes very difficult to distinguish it from the originals. Text generation also comes in the same way. We will go there because it's on ChatGPT. So this is what happens when, as I was talking about MNIST, this is the MNIST-like data generation by generative adversarial networks. You see, I'm just showing you first 50 epochs. For the first epoch, it was almost a noise of pixels, right? Gradually, the neural network is learning to arrange these pixels suitably so that it can make up these digits. And do you know what is the main idea? The idea is these digits that it is generating are not the carbon copy of the digits that has been shown to it. So it is the deep generative model is being shown with a lot of images. It will generate similar images, but not exactly photograph. The images will be similar in spirit, but not the exact duplicates. They will be somewhat different. And if you look at them, it will seem as if some other user has written these 0, 1, 2, etc. This is a very primitive thing, and everyone can nowadays do it on their desktop by programming or simply treating a GAN like network. But from there, we are going towards this sort of conditional generation models. This is also very simple nowadays. This is the source. And what if the visual style of these people, these are the according to their gender, age, hair length, etc. What if we import that style onto this source? How it looks? This is very, very simple, and it all this started from the 2017 ICCB paper on CycleGAN, where the visual content of an image is being translated into another image, and the conditional generation is used. Now, this is, I'm talking about 6 years back from now. To 2017, the first paper came on this. 6 years in machine learning area is like 6 yugas. So now people do it on focal style actually. So what you are seeing is style of an image is being transferred into another image. Now what they do is focal style transform, for which I also have a demonstration, but not here exactly, not within the slides. So I can transform the style of Mr. Bachchan into my voice. So the same lecture will be delivered by Amitabh Bachchan. Recently, just 3 months back, Amit ji issued a statement on Reddit that no commercial company should use my voice. Otherwise, by now a handheld app would have come. All of you would give your statements in Amitabh Bachchan's voice. That is the vocal style class. Content is yours, voice is somebody else. Yeah, and singers also. So I can have his voice actually, and I can sing similar very nice Tego songs in his voice. It's possible, but then there are a lot of dangers associated. I am calling bad names on a guy on phone, and my voice is of somebody else. The police comes and harasses that person. It's also possible. Anyway, so a little bit of technical details. I will speak many of these. So the idea of probabilistic generative modeling is that you have real-world observations and you have synthetic observations. Real-world observations are what? These are like images to the training. These are data points. Every image is a piece of data. Okay. Now, computer scientists call them data points, data items. Statisticians call them observations. Same thing. So from the real world, real images are coming, and the model is the machine learning system. Model is a very favorite word for statisticians. They call it model. It's not a rank model, but this is a deep generative model. So the model gives out synthetic observations or artificial instances, and the idea is the goal of modeling is to match them, right? And from density estimation context, the probabilities, underlying cumulative probabilities should be same for both. And how many of you have had a course of numerical methods? Many of you, numerical analysis. What we do, we start with a very simple trial solution, and then we go on iteratively refining that trial solution in Newton's method or Gauss-Seidel method. Every iterative method works like that, right? Similarly, the first generation deep generative models, now we are in the third generation actually. And first generation was only in 2014. So the first generation deep generative models, what they tried is, they started with some very easy probability distribution like this uniform density function, and then over time they go on deforming this distribution to fit to the distribution of the observed data. And the neural network basically transforms one such easy, this is a very simple Gaussian distribution, and this is the neural network transfer function. So the neural network transfers this sort of a very easy Gaussian density into an output distribution like this, which could have multiple ups and downs or multiple peaks. Let me tell you what it means by learning distribution with a neural network. You can view every neural network as a function. Okay, y equal to f of x. As simple as that. X is the input, which could be in Rp. Y is the output, which would be in Rn. N and B might be same or different. Nowadays, for example, I was showing you this. An application of deep generative model is 20 years before from now, maybe 10 years before from today's date. Nobody could think of it. You have a 1 million dimensional array. That array is basically a 1 megapixel camera image. Now write a computer program or write a function which will convert these 1 million pixels into 10 words. And these 10 words should describe what is happening inside the image. Okay. A mother is cooking food for her child. This sort of description should come out according to the theme of the image. Now, a neural network can do that. The input X is that one-dimensional array, and the output Y is the 10-dimensional, 10 words stacked together. You get my point? So, let us assume this is a neural network. Its input is 25-dimensional array. 25-dimensional array with only zeros and ones in there. Okay, so R25, but binary basically. I pass it, and initially I generate this array from a uniform distribution. Uniform distribution means every component can be 0 or 1 with 50-50 probabilities, 50% chance. I pass it to the neural network. The neural network processes these components through weighted sum and thresholds. These are the basic operations, thresholding. Ultimately, and outside also it is thresholded when it comes out, it's also a 25-dimensional array containing other blacks and whites. 0 means black, 1 means complete white. When I fold it in the form of this 5x5 array, my expectation is I have a 25-dimensional array. I can fold it as a 5x5 matrix, yes or no? This matrix should have a dog-like shape in it. If we do not see that dog-like shape, because I have in my possession some of such 5x5 images with a dog-like shape in between. So I can match with those images. If there is no dog-like shape, the neural network will be punished. How a neural network is punished? By changing its weights and bias and other parameters inside through a method called backpropagation, which is basically a nice manifestation of the chain rule of calculus. Okay, so we go back and change all the weights and biases, and we continue to do that until ultimately, when this training process converges, you will, as input, provide a uniformly distributed 25-dimensional array of zeros and ones, pass it to the neural network. The neural network will arrange these zeros and ones in such a manner that when you fold that output 25-dimensional array into a matrix, you will see a dog-like shape. Sometimes maybe with a tail. Am I clear? When that happens, then we very dramatically we say the neural network has learned the underlying distribution of all dog-like shape images. The neural network is converting the 25 variate uniform distribution into a distribution that best approximates the probability distribution of all such 5x5 images with a dog between. Middle. Am I clear? This is one very simple example of a probabilistic neural network, which is actually taking the difference between the generated distribution and the original distribution, and then backpropagating that to tune the weights of the measure. In deep generative models, one of the best success came in the form of generative adversarial networks. This method rose to prominence in 2014 from Machine Intelligence Laboratory, MILA, in Canada, and University of Toronto, of course. And the first author was a student like you, I mean, somewhat older, maybe he's 26 or 27, young Goodfellow. Goodfellow is like a superstar now, of course. And this particular generative adversarial networks are very easy to code, very easy to use. Although, like all machine learning algorithms, you need to pay some price for that. I mean, price in terms of issues like unstable training, mode collapse, which I will little bit try to discuss. But what is there inside is, in a generative adversarial network, there are two neural networks. One is called generator, and one is called discriminator. The generator takes random noise as input, converts those random noise vectors, which would be simple 100-dimensional vectors sampled from a Gaussian distribution. The generator converts these vectors into matrix shaped or square shaped images. Nowadays, rectangular shape is also possible, so it generates images out of that. And there is another neural network called discriminator. The discriminator's input is an image and output is a score. That score could lie between 0 and 1. The discriminator tries to judge if the generated image looks very similar to these original training images at the disposal of the discriminator. If yes, the discriminator gives it a very high score, otherwise it gives the generated image a very low score. And the discriminator has access to real training images or example images, but the generator doesn't have access to these training images. These two neural networks, we say they are in the adverse mode of competition. What does that mean? That means the generator generates images, tries to fool the discriminator with the generated images. The discriminator initially catches the generator up in a very easy way and gives the generated images very low score. But gradually the generator improves and tries to fool the discriminator. The discriminator sees more real-world images. It enhances its level of making finer distinction between the images generated and the images coming from the real world, and tries to catch up the generator. And so these two neural networks, from game theoretic terms, we say these two neural networks are playing a two-player zero-sum game. Okay, and this zero-sum game is something like that, where if one player gains 5 points, the other player will lose 5 points or gain minus 5 points. So their net profit is always 0. Okay. Ideally, through this competition, both the networks should improve actually and reach a state when it is not possible to improve any further without deteriorating the other network. This state we call Nash equilibrium. Okay, in the name of the famous game theorist Professor John Nash. So the generator is like this. These input vectors are the code vectors which are provided to the generator, and the generator corresponding to each of them is expected to create such images. Okay. So the neural network generator is like this, and this generated image should be very close to the real world example images that are being shown. On the other hand, the classifier, when we use neural network as a classifier, then when we provide an image like this, the neural network should show that if this image is 1, that's why the first class y1 corresponds to 1, that is 1, and other classes are 0. So these two neural networks are distinctly different. Okay. The discriminator, on the other hand, takes the image as input and gives it a score. If it is a very nice image, very high score, otherwise very low score. Clear? Okay, I'm just trying to give you a general method of training this. So the discriminator training is, initially the discriminator is like the teacher or like the critic. It has to catch up the generator. So the general algorithm is given a number of positive examples. Positive examples are taken from the training set. Randomly generate a set of negative examples. Positive examples means very nice images coming from the real world. Negative example means this sort of very poor images which are non-realistic. Where from these images will come? These images will initially come from the generator itself. The generator is initially untrained. So the untrained generator will generate this sort of images, and the discriminator will have these combination of these two groups as its training set. It will learn to distinguish between them. Finally, when the discriminator is trained, it will be used to train the generator. I'll just skip some. So this is one idea, that the generator generates an image, the image goes into the discriminator. If the discriminator is already somewhat learned, see, before teaching the students, teachers need to be learned. Teachers need to be learned, right? So discriminator is like the teacher. Initially, the discriminator is trained. Once it is trained, now the generator is generating its images. Images are fed into the discriminator. The discriminator is giving a very poor score. These images are not shown to the user. Now the generator updates its weights and biases so that it can generate very nice images, and the discriminator score may also update, as you can see here. This process goes on. Okay, so the algorithm is initialize the generator and discriminator. What is neural network? It's a function. It's a highly adaptive function, same as generator and discriminator. They have their own weights and biases. With these weights and biases, their initial random weights and biases, they are initialized. Then in each training iteration, we sample some real objects, and the generator generates some fake objects which are initially very bad. Then the discriminator updates its weights, because the discriminator is trained on this sort of training set containing 1 for these images and 0 for these images. So the discriminator learns, okay, if this image is very good, beautiful, I should give 1, otherwise I should give 0, and so on. Then this updated discriminator is fixed, and the generator is now updated. The generator generates its own images. These images are presented to the discriminator based on the feedback or score from the discriminator. They are updated. Once the generator is updated, this updated generator is again used to generate new and improved set of images. And the discriminator also enhances its ability to finely distinguish between these two classes. Are you getting my point? Teacher has improved. Earlier, The teacher was awarding 5 out of 10. Student was very poor. So student is scoring 4, 5 out of 10 for an essay. Now that based on those numbers, the student has improved. The teacher is giving, oh, acha, khub bhalo likheche. Student teacher is giving about 8 or 9 out of 10. Now the teacher goes and attends another workshop outside and sees the board toppers from other schools. আচ্ছা এরা এত ভালো লেখে তো 8 দেওয়াটা বাড়াবাড়ি বেশি হয়ে গেল। So when the teacher comes back after that update, the teacher is again giving 6.5, 7 to the students. And the student is, oh, let me polish my language a lot. Student is also struggling to fetch out more marks from the teacher. I don't know whether our nowadays youngsters can relate this affair or not. It was very realistic for us. Now everyone gets 9.5 or 10. That's the problem. Anyway, so this is the idea in which the generator and the discriminator updates themselves. So this is the learning cycle of the discriminator, and that is the learning cycle of the generator. Okay. There are 4 most important paradigms for deep generative models, which are currently in use. Most popular is, of course, generative adversarial networks. Then there comes variational autoencoder, which tries to, minimize the variational evidence lower bound on the distributions of which are being approximated. Then there comes flow-based models, which use the inverse transform of the distributions, and diffusion-based model, which solves a series of stochastic Langevin dynamics to model the distribution of unknown samples. These last 2 are very involved mathematically, so I'm not going there right now. But the idea is, you see, the idea is always like this. Generative models, what they do, at least what GAN is going to do, what is the main theme of second law of thermodynamics? Order naturally degenerates into chaos or disorder. That means mechanical energy fully converts into heat energy. Heat energy is a measure of chaos, basically, of the molecules, their erratic vibrations, and so on. But it needs a lot of effort to generate order out of chaos or disorder. That's why the conversion of heat energy into mechanical energy is never with 100% efficiency. Heat generative models are trying to do that. They're trying to generate meaningful images from complete noise. You get that? Generating noise from images is easy, but generating image from noise is not that easy and not that efficient also. So there are certain, that's why nowadays the theoretical analysis of deep generative models pursue based on thermodynamic inequalities. There are certain information theoretic inequalities which say, although the results are enormously good for our purpose, because usually the companies employ huge computing power, but the crux idea is that it can never be as good as the original distribution because thermodynamics prohibits. There are certain fundamental laws of physics. Well, I'm not going into that. That's a very, tentative discussion, though. So why we use deep generative models to avoid class imbalance problems in several real-life classification scenarios, like, class imbalance is a very big issue. One class has very few number of samples compared to the other class. Any rare event detection of nodules from the lungs of people who smoke. Nodules are indication of onset of lung cancer. Always, and fortunately, the benign class is very big compared to the disease class. Everywhere, rare event means it could be a credit card risk, which could be, and we, for example, we did a project with NPCI, the National Payment Corporation of India. Before doing that project, I have no idea that if I gift my wife something, let's say some necklace or something, by paying by Pay or InPay or something, a copy of that transaction is stored in the NPCI server. So where from I bought it, who am I, where is my location, what is the my credit card transaction ID, everything is in their disposal. So what they did is they take up these transactions, and the NPCI wants to, classify all these online transactions into 2 classes: fraudulent versus genuine. Because Indian banking sector loses huge amount of money for compensating customers who are victims of fraudulent transactions. Are we clear? Now the biggest irony is, in 1 week, that was pre-COVID period, I'm talking about 2018, in 1 week, the number of transactions happening in NPCI server is 3 crore, about 3 crores. And among them, the amount of fraudulent transaction is about 4,000 to 5,000. So you see the difference between the sizes of the two classes. You have two classes. One class 3 crore, another class 5,000. So this is very difficult situation. And the classifier is usually very much biased towards the majority class. Whereas if you have 4 in one class, 96 in the other class, and the classifier misclassifies all the 4, its accuracy is still 96%, although its use is 0 actually. So what we do is, for that minority class, very important information is always with the minority. So with this minority class, we try to synthesize artificial samples in the minority class to populate it. This is called class rebalancing. In case of image, GAN or similar DTMs could be used for populating the minority class so that the classifier may not get biased. Then there came other important applications like text to image, style transfer in painting, super resolution, all these things. You have these Prisma-like apps on your mobiles. You can uh, convert your face into how you look like when you are 80 years of age. All these are in the backend running in this very style transfer GAN or style GAN or similar architectures. Virtual try-on is there in fact. The virtual try-on is like nowadays the e-commerce websites, you buy your t-shirt and you upload one photo of yours in Amazon virtual try-on. It will show how you look like when you wear that t-shirt and in various poses, in various backgrounds. That is called virtual trial room. Okay. Similarly, many applications are also there, but the biggest one is when the world was taken by storm with large language models. Now I'm going to large language models. Large language models are typically meant for text generation, text classification, textual inference, and their training data is the entire internet. Many databases available on the internet, especially since this one is on ChatGPT. ChatGPT, the internal large language model is GPT 3.5. By now, everyone knows that, right? For GPT 3.5, the training data was actually the Wikipedia database and many others. Wikipedia database, all the Wikipedia articles they trained actually on that. Many others. Training means you will show examples of text documents. Based on that, the large language model will generate its own text. Like GAN, you are showing GAN many example images and it is generating new type of images. Similarly, large language model will generate new type of text which could be conditioned on some specific purpose. Like the text could be an answer to your question. The text could be summarization of a paragraph. The text could be something else, like it could be the caption of an image and so on, right? Usually, nowadays, what we do is we have a single large language model and we can modify it, and single large language model trained on a huge training set, and we can modify it for multiple different tasks, like this question answering, like a chatbot, like this summarization, like the sentiment analysis, like what is the sentiment associated with the text. If the user is saying something, some tweet, is this tweet in good or bad emotion? It's very important because based on that, share prices go up and down. Okay, I will tell you later. But this model in between, which is being customized for these different tasks, is usually called foundation model. Have you heard this term, foundation model, which is basically the uh, foundation brick of in ChatGPT-like system? And all it works based on this famous quote by John Ford in 1957, you shall know a word by the company that it keeps. So text generators softwares or this sort of deep learning systems are extremely keen on learning the contextuality of each word by looking at what are the other words sitting next to it and before it. বোঝা গেল? একটা শব্দ কোথায় ব্যবহৃত হচ্ছে। Based on that, it learns where to reuse it. Okay? Alone a word has no meaning. The word is always related to its neighbors, and the neighbors actually fix up its meaning. This is clear, and it will be more clearer with this. But before I have to go any further, let me tell you how we exactly handle, how handling text is different from handling images. So the recurrent neural architectures try to handle sequential data. What is sequential data? Sequential data the data is time stamped. So the data is coming, t equal to 0, you have something, t equal to 1, you have something, t equal to 2, you have something. And what comes at t equal to 2 may be dependent on what has already appeared at t equal to 1 and t equal to 0. So it's a sequence of data items coming. These data items could also be, uh, images, text. Text is always sequential because the sentence is of course sequential. You read it from this side to that side, most of us, right? And when you read it, the earlier words determine what is going to be your next word in most of the cases. So if they maintain a sequence, that is where they are different from other data items. When we say we are going to classify the iris flowers, iris data set you might have heard many or MNIST, we are going to classify each image of MNIST into 10 classes, 0, 1, 2, 3. That is basically an optical digit recognition system. In optical character recognition, we would have 26 classes. We are recognizing each character. So the characters can come in any order, right? প্রথমে একটা A এলো কি বললো এটা হচ্ছে A, তারপরে Z এলো, তারপর X এলো, এরকম হতে পারে। They don't maintain any time temporal order, but sequential data always maintain temporal order. And therein lies some difficulty. I'll just show one example if this is visible. Suppose we are talking about a ticket booking system, railway reservation system. And somebody writes this sentence, I would like to arrive Taipei on November 2nd. Benign sentence. Now, this is the text that the user is going to type. The user is not going to fill up an online form. There is a chatbot on the railway end, and there is a user who is talking to the chatbot. Now, from this sentence, the railway ticket booking system should know which one is the time of arrival and which one is the place of arrival. Okay, so there are two slots that ultimately will be outputted from this internal machine learning system. One is destination and one is time of arrival. So the destination is Taipei and time of arrival is November 2nd. Now, suppose this is a neural network. This neural network actually has this sort of thresholding by sigmoid nonlinearity, and these are links through which these x1 and x2, these are your sequential entities which will flow, which will get processed in this network and give you y1 and y2. The very simple network. Input is a word like Taipei, and each word has to be, by the way, in case of text, every word has to be converted into a vector of real numbers or some kind of numbers. Because ultimately neural networks and computers understand nothing beyond numbers. Are we clear? So what happens is how to represent each word as a vector. There are various ways nowadays. When we were working, let's say, 14 years back from now, options were very limited. So one of encoding is one. You can have a lexicon. Lexicon means this sort of collection of words, apple, bat, cat. So you have a very limited vocabulary, and size of your vector is the lexicon size. The dimension corresponds to a word in the lexicon. So naturally, apple, when you are talking about apple, apple will be converted into a vector like this. Why this vector? Because apple comes here as number 1, so this is 1, all others are 0. Similarly, bat, cat, dog, elephant. This is a simple one-hot encoding from a direct limited vocabulary. Is that clear? Okay. Then beyond one-off encoding, you can have word hashing. Like you can have this sort of words at your disposal. And word hashing means the last word could be something which is not in your vocabulary. And word hashing means you will take this sort of a vector of size 26 into 26 into 26, 26 cube, and you will take all the syllables of trisyllables that arrive in your word, that appear in your word. So if you are talking about apple, this APP is 1, PAB is 1, PP is also 1, all the rest are 0. This is just to show, tell you in transformer and in all large language models, the text Now coming to here, suppose I give this type A. So the output is a probability distribution that the input word belongs to these two slots. One slot is for destination and the other slot is for time. So it should be like this, destination and time of departure. If type A comes and if the neural network is functioning correctly, then we expect here the number that appears is 0.9 or 0.95, and here it's 0.01 or 0.001, something like that. 0.9 means the neural network is telling you with a 90% probability that this is the time of arrival. Are we clear about it? So the outputs are probabilities that are being shown. So arrive type A on November 2nd. Arrive should be classified as other. Type A is the destination. On should be other. November and 2nd should be time. Okay. What is the problem in this approach? So we clearly see, okay, it takes up words and classifies each word into this, whether they fall into these two slots. The problem is if this sort of a sentence comes, leave type A on November 2nd. Now the problem is this, for this case, P is the place of departure, not the destination. So how do you understand that? So you cannot treat each word separately. Is that clear? If you try to treat each word separately, then you cannot distinguish between these two. You have to look at what is before this. In one case, arrive and in one case, leave. So these two words, arrive and leave, hold the clue that whether the type A is the time place of arrival or place of departure. So neural networks need memory. Memory means it cannot be such that the something comes and I immediately classify it and I am done. It's not like that. I have to see what was before them and what is going to be after that sometimes also. So I need to hold that thing in the memory. Is this clear? And the recurrent neural structures hold the processed things inside the memory. So whatever comes here goes and gets stored in the memory elements like this. And next time, they are also used for further processing. Memory can be considered as another input. In all large language models, which are built on some structure called transformer, the same philosophy is actually followed. So the example is, suppose all the weights are 1 and there is no bias. Weights means x1 coming from here, x2 coming from here. So the input is simply x1 into 1 plus x2 into 1. This is the input to this structure. And here, this is linear. That means its output is also x1 plus x2. Its output is also x1 plus x2. Think of it as a very simple network. Okay, you are familiar with circuits and networks to some extent. It's an extremely simple thing. So all the weights are 1 and there is no bias. All activation functions are linear. That means there is no sigmoid, nothing like simple linear things. Suppose the input sequence is like this. Initially, x1, x2 both are 1, 1, then 1, 1, then 2, 2. So a sequence like this comes. Recurrent neural networks are the building blocks of transformer models. So how will? So initial values are zeros. Can you see these slides properly? I'm not very confident. So initial values are zeros. Then 1 and 1 comes here. So they become 2 and 2. How they become 2 and 2? 1 plus 1. Every case, right? These 2 and 2 similarly processed here gets 4 and 4. Right? This is how it moves through the neural network. So the output sequence is 4 and 4. Right? Now, these 2 and 2 are also stored in here. These memory elements, what they hold, is called the hidden states. Okay? So they hold these 2 and 2 as a hidden state. And next sequence element comes, which is 1 and 1. So it becomes 6 and 6. And finally, the output becomes 12 and 12. Do you know why it is 12 and 12? So you see, 1, 1, these 2 and that 2. So 2, 2, 2, 6. Similarly, and 6 and 6 makes it 12 here, makes it 12 there. So the output sequence is 12 and 12. Is that clear?
Yes.
Next time what comes?
6, 6.
2 and 2. And already what is there in the in your store? 2, 6 and 6. So it becomes 16 and 16. 6, 6, 12. 2 and 2, 4.
12 plus
12 plus 4, 16. Is that okay?
Yes.
Output 30 to 30. Now, if you change the sequence, it's a beautiful homework. Actually, these slides are for you. I will give it to you, this participants. If you change the sequence, if you would have 2 earlier, and then 1 1, then 1 1, something like that, you'd see completely different output sequences. So same inputs are coming. If you reverse or if you change the sequence, the output sequence would be different. And that's a very important thing for handling sequential data. Sequence must be, given some emphasis while predicting or while processing the sequence elements. So arrive type A, arrive goes through probability of arrive in each slot. That is stored. That stored thing, next time when type A is being processed, from the earlier processing of arrive, that hidden information should be here and reused next time. That is where the connection is being made. Okay, type A, before type A, there was arrive. The মুশকিলটা হচ্ছে আমরা যেভাবে ভাবছি textual terms এ, neural network is not doing it like that. Neural network is doing it to numerical signatures. Okay, earlier arrive was processed, some numbers were generated, those numbers are again coming back when we are processing type A. So probability of type A in each slot, the same network is again and again used. Then earlier 2 slots are affecting the next word on and so on. Coming to transformers, transformers are the backbone of all large language models. And I'm sure I will not go into extreme details of it. Transformers are much like the encoder-decoder architecture. There is an encoder which actually encodes the text into suitable numerical representation. And there is a decoder which will take the current input value of the text and the previous encoded information from the encoder and generate the next values of the text. In fact, how they work is very, very interesting. Let me just, before I go into somewhat detail of it, you have a huge vocabulary and you start typing something, okay? And according to your typing, the ChatGPT or similar large language models, InstructGPT or whatever it starts generating a line of text. How it generates, how it determines, it actually assigns a probability value to all the words in the vocabulary. And maximum probability is assigned with the word, that word is put in the next. Every such large language models have a huge vocabulary associated with it. And it ranks these words according to probability values and puts the highest probable words one after another, based on whatever has been typed or generated so far. So the decoder, we say it acts in an auto-regressive mode. RMN is what you just saw. LSTM is the refinement of RMN, long short-term memory. These were the recurrent neural models for classification, summarization, translation, sentiment detection of text. But their problem is they are not having, they cannot move beyond a certain length of the sequence. When it comes to generation of 3 pages of text or translation or visual question answering from 5 paragraphs of text, Mr. X was born and brought up in Kolkata. After that, he migrated to Paris and he is doing this, that, he opened up a nice restaurant. After 1 page of that, there comes some line which the neural network has to fill up. Mr. X, besides French, is also fluent in dash, in some language. And the neural network, the clue to that is much before this sentence. He was born and brought up in Kolkata, so he should be fluent in Bengali also. I know. যদি যেতে না চায় বেঙ্গলিতেও খুব ফ্লুয়েন্ট হবে সেই যে উত্তরটা ওটা অনেক আগে আছে so it's much before. So the neural network RNN LSTM like classical structures cannot link these big gaps in the text. There is where transformers come, and transformers add very important additional features called attention. Okay, in 2017, Vaswani et al. Vaswani was at that time probably in Google research. Google done a lot of good and bad, both type of things to the world. So I will tell you why some bad things are also there. But Vaswani and this group, In 2017, NeurIPS conference, NeurIPS is the biggest conference in machine learning area. They came up with a nice paper. And machine learning people are very good at giving very nice names, unlike the statistics people. Statisticians are very able. Machine learning people call features, characteristics, which are always very appealing. So the name of their paper was "Attention is all you need." Okay, this is the title of a paper. Attention is all you need, and this paper is now by now, I think 1 lakh plus citations, and based on this is actually the paper based on which ChatGPT was created. All the GPTs were created. Okay? Attention is all you need. What is attention? You will have plethora of explanations in plethora of blogs and other places. But let me tell you, if somebody asks you, hey, you are a computer science graduate, tell me what is attention model? What is attention model? It is a kind of simulation of how human beings read and grasp text. When you are a matured human being, in your early 20s, and when you are reading a line of text, you don't read every word minutely, you don't spell every word, you don't your visual cognitive system actually filters out most of the unnecessary information. What you do is your eye focuses on certain 2 to 3 keywords that they say, maximum 4, 2, 3, 4 keywords. If the sentence is extremely long, then 4, 5 keywords maybe your brain picks up, and the meaning of the sentence is formed in your head based on only those 2, 3, 4 keywords, not the other A and B, off, behind, in front. All these are actually eliminated by your brain. It says, oh, these are the keywords sitting together, so it creates the meaning, and you are ready to respond or react to that sentence. Am I clear? So the attention model, what it does is instead of remembering all the text, it picks up a few very important keywords by giving weightage to different words in the text and reducing the weights of the unnecessary words or redundant words like preposition, conjunction, etc. to almost zero, and amplifying the important words weightage to a high extent. How to give this weighting? That is learned over a huge corpora of text. This is attention model, and our brain does it in a remarkably fast way. Okay, so transformers are extremely, computing savvy. They are computation savvy. Like GPTs have 175 billion parameters to train, 175 billion parameters to optimize. And that's why OpenAI actually took huge amount of financial support from Amazon and other companies to train their this sort of transformers. There are two problems associated with transformer. The encoder is usually BART. BART stands for bidirectional encoder representations from transformers, and decoder, all of us know, uh, generalized, and earlier time it was called generative also, generative pre-trained transformers, as you can see here. Now we call it, because of foundation model, we also call it generalized. And this is the main architecture. Part is taking many lines of text. Part is converting them to suitable numerical representations. These numerical representations are fed into the decoder. The decoder is generating text word by word. When it is generating a new word, not only does it take care about the earlier word which has generated, but also it takes care of huge amount of encoded information from the encoder. This is the complete transformer. If we eliminate the BART portion, we are left only with GPT. Okay. So, yeah. So, if you look at this, the encoder stack models the input and uses the decoder stack to model the output. If you do not have input, you may just want to model the next word, and you can get rid of the encoder side of the transformer. Or you can assume that the encoded information is not needed because the transformer will only act in an auto-regressive manner. In that case, you have something that is called GPT BART and GPT. These are the two main models, and together they are used in lots of places. Okay, attention mechanism is what I just said. The attention mechanism enables the transformers to have extremely long memory because it can attend to focus. It can attend or focus on specific keywords instead of focusing on the entire keyword. So just as an example, say we want to write a short science fiction novel with a generative transformer. Using the write with the transformer application, which is there in this, I mean, as a link here, somebody writes our input is as aliens entered our planet. So this network, actually, if you write a key, some lines like this, the network can fill up a story based on this, based on what you have written. আমাদের ছোটবেলায় স্কুলে মাস্টারমশাই এসে 5টা শব্দ বসিয়ে দিতেন বোর্ডে, বসিয়ে বলতেন বাকিটা নিয়ে একটা গল্প লেখো বাংলা ক্লাস। Similar to the English class also. So if somebody writes as aliens entered our planet and the transformer output, this is truthfully from this software, and began to colonize Earth, a certain group of extraterrestrials began to manipulate our society through their influences of a certain number of the elite to keep an iron grip over the populace. Okay, so the story is a little dark. It's about how extraterrestrial people are grabbing Earth. But it is interesting to note how the model generated it. As the model generates the text word by word, it can attend or focus on words that are relevant to the generated word. And this attention is being given through weight. It's a simple mechanism of weighted sum where weights are modified on the run during the training process. Okay, so the ability to know what words to attend to is all learned during the training through the same back propagation algorithm. So if you look at this, I don't know whether, so this is how the words that are being generated are linked with the words that came earlier. Okay, I'm sure you cannot read it, so I will skip because I mean the online people can still see that. But attention mechanism can actually extend your window to any size of the sentence, and that is the biggest advantage of it. So attention is all you need. That's once again the paper, which comes from here. And so this is where the encoder and decoder steps are coming in face to face. But let me tell you, this whole process, these blocks that I have tried to draw here are extremely difficult and computation savvy. They require, I mean, training 175 billion parameters is not good enough. So I will skip some of the details here and go to other aspects. But before that, as a relief, let me tell you, how many of you know FLOP? FLOP, flops of calculation in students.
Floating point
Floating
operations.
point operations per second, right? You know that? So how many of you have heard of Fukuba, the supercomputer? It was used to be very good. Now it has lost its first place from Japan, probably. And Fukuba could execute 442 petaflops of calculations. What is one petaflop? এগুলো জানার কথা। What is one petaflop? 10 power 15, right? 15 zeros, right? So Fukuga could do one petaflop calculation. To train GPT-4, which is coming, you need some computational efficiency or power, which is 30% or 40% of Fukuga's current, that amount. It's not very high. And we say, I mean, the media, the way media report science is extremely poor actually. The way media report science is something like that. With GPT-4, we are on the way of mimicking human verbal ability, human takes the decision-making power and so on. You see, compared to Fukuga, what you are carrying between your two shoulders, that is this human brain, it's very difficult. It's a thalamus. I mean, it's a form, not exactly a computing architecture, but if you try to mimic human brain as in terms of computational ability, parallel processing system, then the model tells us human brain, and Fukuga consumes the power which is sufficient to light up a 10-story building actually. Got it? Human brain consumes 10 watt of power, electric power, and all the electric impulses moves over it. it computes one exaflop calculation. Exaflop means 10 power 18. I mean, if it has to model, then all of our brains are doing computations in that way. If we even take some more baby steps towards human brain imitation, what will happen is very difficult to tell. Do you know? So the transformers are generating text. How many of you know when you write something, suppose you want to write a dissertation, you want to write a report, and you say, oh, I'm really lazy, so just let me write this. Oh, what is that story? I will say, write 5 sentences about compiler construction, or some of your textual things. ChatGPT will write that. 5 sentences, 10 sentences, 1,000 words. You can write. You can then copy from ChatGPT. Just check. There is no watermark, nothing, at least visibly nothing. So you have ChatGPT. Let it write the first few paragraphs of your thesis or dissertation. Copy it to your original text. How can we differentiate whether it is? How can your teacher differentiate and give you 0 marks for it? Who knows? কথা বোঝা গেল চ্যাট জিপিটি কিছু একটা লিখে দিতেই পারে আমার লিখতে ইচ্ছে হচ্ছে না চ্যাট জিপিটি বলা হয় তুমি লিখে দাও তো so chat gpt writes it down. Now that text goes to your teacher, and if your teacher is smart enough, he or she can actually catch you up. How? Yes. Plagiarism checker impossible. If you go for common plagiarism checkers like Authenticate, Turnitin, etc., they will give you a full clean sheet. Okay, it's a very original text because ChatGPT is actually mixing from many different sources. The best way is, and this is a tip for the teachers also, the teacher will copy that same thing into ChatGPT and ask, have you written it? ChatGPT will say, yes, I have written it. Because, and this is very, very interesting, because the words, the way the words ChatGPT generates, inside the arrangement, sequential arrangement of those words, there is a watermark of ChatGPT, which is not revealed to the common users. এটা যে কেউ করে দেখতে পারো a paragraph which is actually written by you versus a paragraph written by ChatGPT, ওকেই জিজ্ঞেস করো তুমি লিখেছো ও একটাতে হ্যাঁ বলবে একটাতে না বলবে, because it catches up that watermark hidden. By the way, it should be more than 4 lines. ছোট হলে একটা টুইট বলতে পারবে, কিন্তু 4-5 লাইনের বড় টেক্সট যদি হয়, okay if I occasionally speak in Bengali and a lot of you understand, anyway I'll switch to English. But if sometimes if it is more than 4 lines, it definitely catches it. So I will skip many of these unnecessary details on the this is basically if somebody wants to learn how a transformer really works, then there is very nice things here which I don't want to bore you up with this mathematics and other things. So I will skip most of this. Is the foundation. This is basically how, if 2 sentences are generated, the cat, one sentence is the cat sat on the mat, and the next sentence is the cat lay on the rug. So the cat, the identity of cat, what are next and before, all these things are identified by generating proper attention weights, and how that is done, that is shown over here. So generalization of large language model is the foundation model. So foundation model is here. You have huge training data. Foundation model is trained once for all, and then the foundation, that training is used to accomplish multiple different work tasks. That is where foundation model comes. In fact, GPTs are the foundation models. T5 text token generation from text transformer, that is also a foundation model. And this is, it can do multiple different jobs, like translate English to German, the code a sentence, then you can summarize some text and so on. There are a few different types of LLMs available. One is the zero-shot model. It's a large generalized model trained on generic corpus of data that is able to give a fairly accurate result for general use cases without the need of additional training. What does that mean? That means once it was trained with huge corpora of text, and then it can generalize its training to many other tasks, to many other users. This is called a zero-shot model because shot means need of additional training data. It doesn't really need additional training data to work in some manner. Then there is fine-tuned or domain-specific models, like where you can use the zero-shot model like GPT-3 for more domain-specific tasks. Like if you look at Codex, Codex is a domain-specific large language model which generates computer programs in any language. Okay? You can write a C, Python, Fortran, any kind of code with Codex. Uh, Then there comes language representation model, like where you want to code and represent a certain language in terms of certain things. So when we BART has to be connected with GPT. If you want to mold GPT for some new language like Bengali, then BART has to be trained on Bengali corpora, and then BART has to be interfaced with GPT, and then only GPT can be customized on that. Then there comes the more dangerous one, the multimodal models. GPTs are originally elements were specifically tuned for text, but multimodal approaches now take into context both text and image. So not only a story, GPT-4, which is going to be launched, can write a comics for you. Comics, like a new Tintin page with Tintin and fictitious text and stories inside it. And OpenAI at least says it operates on ChatGPT by using reinforcement learning. Reinforcement learning is something like in normal supervised learning, what we do, we show a lot of examples. Okay, these are fraudulent transactions, these are genuine transactions. By looking at such examples, the machine gradually learns how to finally distinguish between the two classes. So when a new transaction comes, it applies those finer distinctions that it learned and then puts that new transaction into one of the two classes. That means there is a guideline from some supervisor that these are good and those are bad. These are fraudulent, those are genuine. On the other hand, in reinforcement learning, in reinforcement learning, there is some agent which is performing some action on the environment in which it is put, and as a return, it receives either a reward or a penalty from the environment. Based on that reward or penalty, it plans its next course of action. Okay? The kid is locked in a room. In that room, there is a nice ping pong ball, and there is a bright candle flame glowing. So the kid goes to the candle flame because it's very bright. It's attracted by it, tries to touch it. Few times it gets burned, cries. Learns it's a dangerous thing. Better to keep away from it. Better to spend more time on with the ping pong ball without the input from parents. This is a learning through direct interaction with the environment. আমরা বলি না যে জীবন ডাইরেক্টলি যখন শেখায় তার চেয়ে বড় শিক্ষক আর কি আছে। Reinforcement learning is much like that. And in case of ChatGPT, they say, I mean, this sort of large language models, they say they try to use this human in the loop reinforcement learning. So somebody is writing something, and then ChatGPT, OpenAI actually hires a lot of content filtering people, especially from Middle East and Africa, Ethiopia and other countries. They hire a huge number of content filters. These content filters, their job is to provide positive and negative feedback on the content that ChatGPT has written. When it was launched, I remember in 2023 January, I was giving some offensive keywords and it was writing on them. I also gave some keyword like write down the formula for Molotov cocktail. You know, Molotov cocktail, it's a dangerous bomb. And it was very fluent in writing that out. After 1 month, I could not make it do that because it was saying what you are giving is prohibited, I cannot write it, etc. By that time, some human feedback has gone that it must be stopped from writing such dangerous recipes for making bombs. এসব তো হবেই, কিন্তু লোকজন জানতে চাইবেই সাথে সাথে কি করে বোমা বানাতে হয় লিখে দেওয়া হবে। Anyway, I will just to tell you one basic thing. Till now, actually, deep neural nets for image data, there is very advanced mathematical structure for image data. And a lot of theories are coming up. Contrary to that, for sequential data like text, almost no theory is there. However, now people have started making theoretical foundations for large language models also. Uh, Language they see as algebraic. In algebra, you can multiply two symbolic variables, x and y, becomes xy. Similarly, in language, the multiplication could be replaced by an operation like concatenation to tell you the spirit of it. Like red into fire trap is just like red fire trap. Okay, Red Riding Hood, something like that. So we are concatenating words together as we type this sentence. That is algebra. Another word for this kind of structure is also called compositionality. So where things compose together to form something larger. Since language is algebraic, it's intriguing to think about what kind of mathematical tools are at our disposal. One could, for instance, revisit old ideas from abstract algebra to see old ideas from group theory, homomorphism, etc., to see if there are any new insights. But then, for example, an algebraist might try to formalize the first code. First code is what? A word is identified by the company that it gives. Okay, by simply identifying the meaning of a word with something like a two-sided principal idea associated with that word. And the principal ideal is the name given to a certain algebraic structure. This is, I don't know how many of you are fluent in ring theory or something. Have you gone through abstract algebra course by this time? Not yet. Then I will simply skip it. So basically the idea is if red is a word, what are the other words coming mostly composition? Compositionality of red is extended most frequently to what other words? Like red ruby, red blooded, bright red eye, red meat. You see, but red hot dog very rarely spoken of. So what are the maximum time? What are the words coming up with red? If x is an element in the ideal, then any expression obtained by multiplying x on the left or right with some other element is also an ideal. So a principal ideal is a set that attracts everything that has x in it, like a magnet. Okay, like find subsets in which x is always an element, something like that. It has its computational signatures also. So the concept of a word like red is thus identified with the principal ideal consisting of all expressions that contain red ruby, bright red ruby, and so on. Not only is a language algebraic, it is also statistical. This is the next part. The expression red fire truck occurs much more frequently in English than red idea. Red idea শব্দটা খুব কম ব্যবহৃত হয়. Red fire truck is much more common. This also contributes to the meaning of the word red. The probability of someone saying I have a red idea is quite small. I have something. Before that, if you want to use a color, red might be the least choice. Okay, so as the number of times the expression has been uttered is pretty low. So let's then hold on to our algebraic inspiration but switch off to a different set of mathematical tools. One that is better suited to merge both the algebra and statistical structures in language. That is called category theory. Since you are not much into abstract algebra, let me not waste more time and let's try to conclude sooner. So category theory is a finer version which comes from abstract algebra and operative theory. And nowadays, we envisage the large language models could be theoretically backed up by using nice ideas from category theory. There is this very nice paper which actually gives you a survey of how category theory of language could be used from syntax to semantics. Every language is a category, and then they have this sort of one of the most important results in category theory in the form of Leonida lemma, which tries to figure out these principal ideals from subset of the vocabulary and so on, but I'm not going to it. Most important things before I conclude. Are we ethically on the right track? It's a pity that ChatGPT is everywhere. Everyone is using it. And we have heard good and bad things about it. For example, how many of you have heard of Noam Chomsky? One of the leading legend,
Chomsky hierarchy.
thinker, great thinker, Chomsky. Chomsky referred to ChatGPT as kind of plagiator, basically. It's a plagiarizing thing, which is nipping in part the originality the original creativity inside the younger generations, etc., etc. On the other hand, in our times, the smartest, or probably the smartest person on earth, who is a smart guy, one who could very quickly find the solutions to his problem or the problem of human civilization. To me, in my generation or my time, one of the smartest guys, Terence Tao. Have you heard of Terence Tao? Yeah, it's a mathematics prodigy, Fields Medal winner, great number theorist, and so on. So Terence Tao, in March or April, probably first week of April, issued very nice statements about ChatGPT. It is helping him to find proofs of mathematical conjectures and theorems. It is actually verifying what he proposes as a proof, if that proof is complete, if that proof is already done by someone else in some other form. All these things are being verified, etc. So we have a mixed opinion. But then there are very, very dark aspects also. Young LeCun, he was a 2018 Turing Award. Turing Award is the Nobel Prize of Computer Science. So in 2018, the three deep learning godfathers, Jay Fenton, Young LeCun, and Joshua Bengio, they were awarded the Turing Prize. LeCun, when there was a lot of critical arguments regarding ChatGPT, LeCun said 94.7% hate speech are taken down automatically by AI. LeCun hates the Facebook AI research. So a statement like this from him is extremely alluring. But what is the ground reality? ChatGPT no doubt uses unfathomable training data in the order of billions and billions of text documents which are stored in the entire Wikipedia database, which is stored in Yahoo search engine corpus, in many other datasets, Quora, ScienceSphere, PubMed, all these datasets in conjunction have been used. Unfathomable training data. But size doesn't guarantee diversity. That's the most important point. Who are the people? Who are the people who most often write Wikipedia articles? These are people from advanced countries. These are mostly male, not even female. If you look at the percentage, who are contributing articles to internet, who are contributing articles, how many articles in Wikipedia is from marginalized communities, some Ethiopian tribe, some Indian tribal society, Lodha, Shabo, Shuli, Pol, Bhil, are there representations? No. What I was telling you, netizen versus citizen. So whenever there is an election in the society, I mean, big city, everywhere on earth, actually, citizens are much more weighted and attended than netizens. So netizens are much more weighted and attended than citizens because their opinions play a big role. Static data changing social views. Social views keep on changing about different events. We look at what is happening in France itself now. Huge chaos has begun there. Okay, there are encoding bias. I'll tell you what is it. Curation, documentation, and accountability is extremely low for many such data, which is against people who are vocal about these things. So recently, Timnit Gebru has documented. Timnit Gebru is a huge name in this aspect. She was the person. She had a PhD from Stanford. She was actually from Fei Li's lab. Fei Li is one of the chief architects behind deep learning development. Gebru was Ethiopian by nationality. She earned PhD from Stanford. She was in Apple, then hired by Google. While in Google, she wrote with her co-workers a paper on how Amazon face recognition softwares are extremely biased towards the white people. And similarly, she is now in the process of exposing in ChatGPT how all the ChatGPT majority of the training data comes from America, US, and how most of the violent keywords like murder, burglary, rape, things like that, all these violent keywords are actually related to the black community. If you ask ChatGPT to write a story on some violence happening in some neighborhood, it will take up 2-3 black Americans as the major characters of that plot. It will never say it's a white person who has committed this crime. Same thing was happening for the Amazon face recognition database. And the most dramatic irony is actually China brought that face recognition software from Amazon, and then they were using that face recognition software for watching the Uyghur Muslim people actually. And then they tortured them, jailed them, a lot of things happened. None of these events were featured in YouTube or Facebook or Twitter because these social media people, the people at the apex body of the social media, actually are governed by the government of the country in which they are doing business. In India, Indian government actually regulates them, and it's the truth. If you post something which is offensive to your government in Facebook or Twitter, you will see how the reach of that post severely, shrinks. You will see 2 likes. If you have 5,000 friends, you will see 2 likes after 3 hours. Why? Because that post hasn't reached people outside. Facebook algorithm somehow regulates the reach of that post. I don't know how, but it does. So the net result is, this is from Timnit Debru's paper actually. The net result is that so Timnit was fired from Google. Timnit, after writing this paper, instantly Google fired Timnit Debru because she was exposing this big bias. And then she came up as she started her new organization called Blacks in AI. Now she's a very prominent name. I first came to know about her when I saw 2021 Nature, the famous Nature journal. Nature published 10 young scientists who have changed the face of the world. In their original editorial, Nature December 2021, I saw 9 of the 10 are related to COVID research. Different types of research. I mean, COVID vaccine. Only one non-COVID machine learning person thing is there. Then I started learning about her background, and she just gave a talk in ISI also, in one of our winter schools. So this is from her writing. The net result is that a limited set of subpopulations can continue to easily add data. এই যে উইকিপিডিয়ায় গাদা গাদা ডেটা তোলা হবে, কারা তুলতে পারবে? তাদের প্রচুর সময় আছে, প্রচুর রিসোর্স আছে, প্রচুর ইন্টারনেট অ্যাক্সেস আছে। আমরা কি একটা মাসাই কমিউনিটি আশা করতে? So who can easily add data, sharing their thoughts and developing platforms that are inclusive of their worldviews. See, history is always the fiction written by the people who have power or who won. You never know the counter story of common people in the time of big kings. Okay? You know what has been written with permission of those big rulers out there, right? So sharing their thoughts and developing platforms that are inclusive of their worldviews. This systematic pattern in turn worsens diversity and inclusion within the internet-based communication, creating a feedback loop that lessens the impact of data from underrepresented populations. And it's much more true. This skewed document set is the training data for LLMs. Okay, various forms of abusive language, harassment against different groups of people that is unaddressed, proliferating harmful content, and in return, work on LLM does not focus on any of these countries, languages, or people, especially Africa, or people for which these platforms are causing the aforementioned issues. In India also, I don't know how many tribal languages have been included into LLMs. LLMs could be locally modified, but we never think of that. We always try to, okay, we have a technology developed in USA, let's dance around it, let's copy it, and let's try it without any further adaptation. So we are not letting our poorest of the poor women in Sundarbans or in Chhattisgarh or in Jharkhand to ask a telemedicine chatbot their problems in their own language. They cannot translate it into English or even in Hindi, if I'm not wrong. So bias represents how much disproportionate weight or fact is there in such, relational opinions or whatever content is being generated by AI. But bias, Google people or Microsoft people I was just giving a similar talk 1 week back, and the Google India director was there, Manish Gupta probably. So I had some argument with him. He finally agreed that okay, we talk about bias, but then I wrote this sentence: gatekeeping is always done by those who are in power. What you call as bias, it's always the rule of power. The person who is in power, his wrongs are even right. That's how the society is run. So in large language models, bias can be included in a lot of ways, like from the data, historical bias, representation bias, which we call as encoding bias, measurement bias, and so on. Then in AI/ML part, where we have algorithmic bias, evaluation bias, application bias, and so on. In the human review part, also some bias can come up. Let me give you some examples. Historical bias refers to the pre-existing bias presently already in our data, which can persist even with the ideal sampling and feature selection. Machine learning algorithm is perfect. Ideal sampling is done, fully unbiased. But historically, our mindset is like that. This bias was exemplified in the study. And if you look at the title of the study, you know what this bias is all about. Man is to computer programmer as woman is to homemaker. This is the bias. The title says what the bias is. Woman is not the computer programmer. She has to be a homemaker. Man has to be a computer programmer. And if you look at this, okay, let me just skip a bit. Where are those lines there? So the thing is, if you ask, yeah. So if you ask this language model to write a story, pre-trained language model to write a story about the family without anything, it writes something like this: my mom is a homemaker, my father is a doctor. Very rarely it will write the reverse. I have never seen. You can try and see. Similarly, when you ask it to predict the sentiment, he loves travel alone. The prediction is joy. She loves travel alone. The prediction is fear. This is the inherent representation bias. She, the gender, she cannot travel alone. There are a lot of fearful factors outside, but he can travel alone, even later at night. This is the bias. And this bias is inherently there in the very corpus of the data that we are talking about. Similarly, we have representation bias. That's what I just said. This happens from the way we define and sample a population to create a data set. The data used to train Amazon's facial recognition, mostly based on white faces. That's why, in fact, this software could not differentiate between black male and black female. For white, everything is right. For black, everything is wrong. And all the violent content were attached to them. Okay. So, and there was a paper, I forgot, I don't see that here, but if you look at it, you will see how much violent terms in ChatGPT, even now, 2022, there was a paper in the Nature Machine Intelligence, which shows how much of these violent terms in GPTs are related to marginalized or minority communities in different countries, including the Muslims, the gays, the sort of blacks, and so on. Whatever is the minority population in any country, the GPTs always act against them because they are underrepresented. They don't have the ability to, put their presence in their training data. Same thing comes from human review also. These are just some examples. So I will conclude now with these few thoughts. Training data must guarantee inclusiveness. If you cannot guarantee that training data, if you cannot guarantee the representation of marginalized communities in your Wikipedia documents, then don't use it to create a GPT for your country. Do not copy paste other technologies. Technology is hardly a silver bullet. In fact, machine learning is never a silver bullet. There is a famous theorem called no free lunch theorem in machine learning. It says every time you gain some advantage, you need to pay a price for that. No one is going to, offer a lunch free of cost to you. If someone does, he will definitely or she will definitely ask for some other vested interest. So Technology is hardly a silver bullet. Efforts to achieve a technological solution to social problems can make things worse. This is also called techno-solutionism. Everything can be solved with technology. This is a very, very bad idea. Okay? Technology is always connected to power, and we need to be very, very awakened to that fact. So much of the current AI technology centralizes power. Who can use, who can, at a mass scale, who can use resources? Who have resources? Obviously, for a poor country or developing country, government has the most of the resources. Simply copying the current trend might cause more harm. Okay, you need to adapt it for your own landscape, for your own people, for your own culture. Most often, one of the severe lack of ChatGPT, seminar on this sort of technologies, is it doesn't understand, and this is something that you young people can probably try your hands on, where you are defining or trying to design local versions of the GPT. It is completely agnostic to cultural idioms in different languages. Language is very, very much well inherently connected with culture. Actually, the same word can be very offensive to some people and very welcoming to some other group of people in different languages. And there are common words across Hindi, English, Tamil, not English, Hindi, Bangla, Tamil, they have common words rooted from Sanskrit, right? Ordering of the words can be something. I mean, when you are talking in English, how many sons and daughters do you have? ChatGPT writes it in English. How many daughters and sons do you have? বাংলায় হলে পারবে ওই শব্দটুকু পাল্টে দিলে কি বিভ্রান্তি সৃষ্টি হবে? All of us know that. Do you understand what I'm saying? So the cultural idiom of language is something that ChatGPT like engines must be adapted to for diverse countries, diverse populations, and diverse cultures, and they do not do that. Okay, how can we build technology that decentralizes power, protects our people, protects all of our people? See, progress is not about copying a US technology. Progress is always about making a society where the most minority people can live with heads up. সংখ্যালঘুতম লোকটাও মাথা উঁচু করে বাঁচতে পারবে এরকম একটা সমাজ তৈরি হচ্ছে প্রগতির লক্ষ্য। চ্যাট জিপিটি বানালাম আমাদের ভারতবর্ষের জন্য ইউএস থেকে কপি করে, এটা কোনো প্রগতি? So protect our people and offer key benefits to members of the marginalized communities. So you have to work in such a way that AI benefits may trickle down to those marginalized communities. So with this message, I would actually conclude. Thank you very much for your patience, and let us open to questions. If you have any question or from online, any question?
এই তো বোতল
Yes, please go on. Thank you. Thank you. আমি কি অনলাইনে শোনা যাচ্ছে? সুন্দর শোনা যাচ্ছে। Thank you, sir. So, thank you, sir, for this excellent lecture. I am personally, please accept my heartfelt gratitude for this. I have one question regarding your beginning slides, earlier slides. So, what I think about, there are two computational models. So, in zero sum game, if I subtract -5, I am taking +5. So, if we can compare these as like two strikers played, one to striker, and ultimately put the ball in the net. So the more I learn, more points I get, and more I get. Close interval of 0 to 2.
of this from the picture of the classification data. So is there anything we can optimize this process so that the generative model will learn quick? This is my first question, because the more we iterate, as the first speaker spoke about the carbon footprints of AI, CO2 equivalent. Optimizing this is my part A of the question, and the second question is, initially I give the image or any data, and it will give a score. For poor classification, it will give 4 score, and the high score is 1. But what if my model, my data is flawed, and from the flawed data, my training is flawed? So if the generative model creates a poor picture, because my training is flawed as a teacher, I will give it more marks.
This can always happen. I mean, let me answer the second question first. Please sit down. We can have a very cozy discussion. So first of all, is if your data is once again imbalanced, you are trying to show, suppose you want to generate apples, images of apples. Now within the apple class, there are a lot of subclasses like green apple, white apple, not white, yellow apple, reddish yellow, not features, the complete pictures. Here the features are also different, yellowish, green, etc. You have only shown green apple, not the yellowish ones, not the reddish ones. So definitely in that case, the network will also generate that one single mode of your training data. We call it mode collapse. Okay, mode means these different peaks of the density function. Now, if only one mode is generated, that means either the training process is unstable or your training data is imbalanced, biased towards that mode only. So this is one thing that very frequently happens. That's why my slide began with the folklore that your ML can never be better than your training data. So it can so happen. Nowadays, what people do is, okay, for the carbon footprint related question is how we can reduce the amount of training data and hence reduce the number of updates of my weights and bias. See, for a human children, for my daughter, one picture of giraffe is good enough. I will show it. My daughter, after 2 months, will go to the zoo and identify a giraffe. Papa, look, that's a giraffe. But for a neural network, I have to show the neural network 2,000 giraffe images. Only after that it will identify one giraffe image. So the methods which try to one particular way is actually what they do is they take different these patches from the same image, and patches are ordered to generate augmentation on the same image and for training or transform into very informative feature spaces, and from just one or two such images, let the network generalize that concept class with minimal weight updates. This area is called few shot training. Large language models like GPT work on zero shot training actually. This can reduce the carbon footprint. Large language models like GPTs try their utmost to reduce carbon footprint because their number of parameters is so severe. Unless they do that, the amount of computation will be completely intractable. Okay. Now coming to your, I mean, this two-player zero-sum model that I was talking about, actually the same objective function is optimized. The objective function I didn't show in this beginning slides because this stuff was on large language models. If you go to GAN and look at the objective function, there are two parts of it, one for the discriminator and one for the generator. These two parts, one part is about maximization and the other part is about minimization, right? And they try to reach a condition like Nash equilibrium condition, where from any further minimization of the discriminator objective or maximization of the generator objective. Generator objective is basically the discriminator score, which the generator tries to push up as much as possible. But any further variation of these two quantities is not possible without deteriorating the other significance. This is called Nash equilibrium. Now, game theoretic framework is not the only one for GANs. Nowadays, people are coming up with advanced GAN-like algorithms where they are using methods from multi-criteria decision making. This is basically a multi-objective state scenario. Okay, you have two different objectives to fulfill. Then what is the best trade-off point you can achieve? So game theoretic setup or game theoretic uh, objective function came because the originators of GAN thought it in that way. Now people are thinking in other ways and they think, okay, game theory is not the best option to optimize objective functions by using gradient descent. That in that way there comes the Wagenstein GAN, which uses the optimal transport like concepts. Are you familiar with optimal transport? So you can search that. Optimal transport is a very old way of mapping one probability distribution into the other actually. It's a 300-year-old problem. And maybe yeah, there are certain measures of dissimilarity between two probability distributions, like the Wagenstein distance and Wagenstein GAN or WGAN. Instead of relying on this game theory, they directly try to minimize that difference between the generated distribution and the original data distribution. That has also one drawback. That has some drawback, obviously. Yeah. This approach can it be solved multi-objective optimization? Yeah, that's what I'm saying. Multi-objective optimization methods, which actually known in the mathematical programming community as vector programming or goal programming in some cases. Okay, they don't call it multi-objective optimization, but it's actually multi-objective. Vector programming approaches now are being adopted for devising more powerful GANs, which have stable training pattern. Usually in GAN, what happens is Nash equilibrium is almost never reached. We are happy when we see generator is generating very nice images, actually. And then we can adopt that generator for conditional generation. Like the generator is generating facial images and very high resolution faces. That person never exists on Earth, but the generator will show a camera click photo. Now in conditional generation, it's very easy for this game theoretic approach. It's very easy to tweak it, like generate images with nice glasses on, Ray-Ban sunglasses on. That's the condition. So imposing such conditions are very easy with the game theoretic setup. That's how it works. Okay. From online.
Yes.
Yeah. Okay.
Is there any relation between HLM and AST?
Yeah. Yeah.
The mic.
There is another control. Shall I use this?
Yes, sir.
Yeah. If you go back to 1980s, maybe up to mid-90s, HMMs, hidden Markov models were the only option for modeling such sequences based on Markovian random fields. But the problem is, hidden Markov models cannot take long-term relations in proper account. The Markov property itself is very restricted from that aspect. It cannot say what is the influence of the second word on the 22nd word in the same sentence. So there are such drawbacks because it cannot store multiple hidden states meaningfully when the window of operation is very large. From that respect, LSTM is very good, and in fact, the HMM-based prediction would be derived as a special case of LSTM, and there are some mathematical studies available, which I can send you actually, or you can find it out how, in what way HMM qualifies as a special case of LSTM, which is of course much more generalized.
Yes. Last chapter ছিল there. How detailed model is learning by reinforcement learning.
Yeah. So once the model is pre-trained, there are still certain, portions of the model that are customized for specific queries. It's like, you see, basically the GPT is the final layers of the foundation model. Near the final layers, when the weights are more When the weights are further tuned, they're tuned based not based on the gradient descent objective function, but based on the rewards or uh, punishments, rewards or penalties, better I say, provided by the human user. So if the human user rates the answers, usually the answers are rated on a scale. If the human users rates these answers on a scale very poorly, then the weights will have a proportionate change near the final layers of the decoder. Otherwise, the weights will not change if the ratings are very good. So based on this is where reinforcement learning comes into play, and human user makes a lot easy, adjustment of RL because you don't really not need to stochastically model the environment to generate the feedback. The human user makes your job very easy. Based on those rewards or penalties in terms of numerical figures, the weights in the final layers of your pre-trained transformer are changed accordingly so that next time the offensive responses are not generated. That's the mechanism basically. Then, I mean, during this phase, the GD modules, the gradient descent modules are not activated. Okay. Other question? Okay, so thank you.
Thank you, sir, for your remarkable research on this topic. Now I would like to call upon our honorable Professor Dr. Navonita Ma'am to felicitate Dr. Sabitan Das.
Let's just have it clear.
Yeah. Thank you so much, Sharon Tom. Accepted our invitation in such short notice. And there is another gift also.
Really,
Okay.
remarkable.
You are the
This
donor.
part of it.
Yeah. Thank you. Sir.